Look up at the night sky, and what do you see? A scattering of stars, maybe the faint glow of the Milky Way, but hidden within that darkness lies one of the universe's greatest mysteries. How did all of this come to be? Galaxies, those colossal cities of stars, gas, and dust, didn't just appear overnight. They're the result of a cosmic dance that's been unfolding for billions of years, shaped by forces so powerful they bend space itself. Think about this. The Milky Way, our galactic home, contains over 100 billion stars, each with its own story. And yet, it's just one of an estimated 2 trillion galaxies in the observable universe. How did these immense structures form? What forces sculpted them into the spirals, ellipticals, and irregular shapes we see today? And what secrets do they hold about the past and future of our cosmos? The story of galaxy formation isn't just about distant points of light. It's a tale of gravity's relentless pull, of collisions that spark stellar fireworks, of supermassive black holes lurking in galactic hearts, shaping everything around them. It's a story that begins in the aftermath of the Big Bang, when the universe was a swirling sea of gas and dark matter, and unfolds across eons as galaxies grow, merge, and sometimes even devour one another. Picture this: 2 galaxies, each billions of times more massive than our Sun, drawn together in a slow-motion embrace that will last millions of years. When they finally collide, it's not destruction, it's rebirth. New stars ignite, cosmic dust is reshaped, and the galaxy that emerges is something entirely new. That's just one of the astonishing truths we're about to explore. In this journey, we'll uncover 50 mind-blowing facts about how galaxies form, evolve, and sometimes vanish without a trace. You'll discover how the tiniest fluctuations in the early universe gave rise to the grand structures we see today, why some galaxies are galactic cannibals, and what the fate of our own Milky Way might be. This isn't just a list, it's a voyage across space and time, a chance to witness the universe's most dramatic transformations. So buckle up. By the end, you'll never look at the night sky the same way again. At first glance, the early universe seems like it should have been perfectly smooth, a vast, featureless expanse of hot gas stretching in every direction. But the truth is far stranger. Even in those first moments after the Big Bang, tiny ripples of unevenness existed, imperfections so small they'd be invisible to the human eye. These minute variations in density, some regions just slightly thicker than others, were the cosmic seeds from which every galaxy, star, and planet would eventually grow. It's almost poetic. The grandest structures in existence owe their birth to the tiniest of beginnings. So where did these fluctuations come from? The answer lies in the quantum realm, where particles flicker in and out of existence in a chaotic dance. In the intense heat of the early universe, these quantum jitters left behind subtle imprints in the fabric of space-time, like fingerprints pressed into wet clay. Over time, gravity amplified these tiny differences. Regions with even a fraction more matter pulled in more gas, growing denser, while sparser areas thinned further. Imagine a stretch of ocean where one ripple is ever so slightly higher than the rest. Given enough time, that tiny crest would gather more water, rising into a towering wave while the surrounding surface flattens. That's how the universe built its galaxies, not from some grand design, but from microscopic imperfections magnified by gravity's patient hand. What's truly astonishing is how delicate this balance was. If those initial fluctuations had been even slightly weaker, matter might never have clumped together, leaving the universe a dark, empty void. Too strong, and everything would have collapsed into black holes before stars could form. Instead, those quantum whispers hit the cosmic jackpot, just enough variation to spark the birth of galaxies, but not so much that they tore the universe apart. And here's the wildest part: we can still see those ancient ripples today. The cosmic microwave background, the faint afterglow of the Big Bang, holds a snapshot of those density variations, frozen in time like shadows on a cave wall. They're the blueprints for everything we see in the night sky, a reminder that even the mightiest structures in the cosmos owe their existence to the quietest beginnings. Dark matter is the universe's best-kept secret, a ghostly presence we can't see, touch, or detect directly, yet it holds galaxies together like invisible scaffolding. Without it, the cosmos as we know it would collapse into chaos. Picture a spiderweb, delicate and nearly transparent, yet strong enough to catch prey midair. Dark matter works the same way, its gravitational pull weaving an unseen framework that guides ordinary matter into place. While stars and gas clouds shine brightly, they're merely the glittering decorations draped over this hidden cosmic skeleton. In the early universe, dark matter did the heavy lifting. As those tiny density fluctuations from the Big Bang began to grow, dark matter's gravity acted like a cosmic magnet, pulling hydrogen and helium gas into its clutches. These primordial clouds, drawn into clumps of dark matter, became the first protogalaxies, the rough drafts of the majestic spirals and ellipticals we see today. What's astonishing is the scale. A single dark matter halo, invisible to telescopes, could stretch hundreds of thousands of light years across, cradling enough gas to birth millions of stars. Here's the twist: dark matter doesn't behave like ordinary matter. It doesn't collide, compress, or glow. It simply passes through itself and everything else, leaving gravity as its only calling card. This means while gas and dust slam together, heat up, and blaze into stars, dark matter lingers in the background, a silent architect shaping galaxies from the shadows. Astronomers call these dark matter structures halos because they envelop galaxies like faint, massive auras, their gravity dictating how fast stars whirl and even how galaxies collide. Without dark matter's steadying hand, galaxies would fly apart, their stars scattering into the void like beads from a broken necklace. The proof is in the motion. When scientists measured how fast stars orbit the centers of galaxies, they found something bizarre: the outer stars were moving far too quickly. According to the laws of gravity, those stars should have been flung into space unless some invisible mass was anchoring them. That missing mass, dark matter, outweighing visible matter 5-1. It's the reason galaxies exist in their current forms, the reason they cluster into vast webs spanning the cosmos. Every galaxy we see is just the tip of an iceberg, with dark matter forming the vast, unseen bulk beneath. And the wildest part, we still don't know what dark matter actually is. Particles, primordial black holes, something even stranger. Whatever the answer, one thing's certain: the universe as we know it wouldn't exist without this mysterious, invisible force. It's the unsung hero of galaxy formation, the quiet giant upon which the visible cosmos is built. Those early galaxies were nothing like the colossal spirals we picture today. Instead, imagine cosmic fireflies flickering in the darkness, each barely a fraction of the Milky Way size. Born just a few 100 million years after the Big Bang, these mini-galaxies were the universe's first experiments in structure, some no larger than 1 million stars crammed into a space barely wider than a modern star cluster. Yet these unassuming specks held the key to everything that followed. What made them so small? Back then, the universe was a cramped, chaotic place. Gas hadn't yet pooled into vast reservoirs. It was scattered in dense pockets like raindrops clinging to a spiderweb. Gravity worked with what it had, pulling together just enough material to ignite a few generations of stars. Unlike today's galaxies, rich with heavy elements from deceased stars, these pioneers were built from pure hydrogen and helium, the pristine leftovers of the Big Bang. Their stars burned hot, fast, and blue, living short, violent lives before exploding as supernova, seeding the cosmos with the first heavy elements. But the real magic happened when these tiny galaxies began to collide. Drifting through the early universe, they were drawn together by dark matter's invisible threads, merging in slow-motion crashes that lasted eons. Each collision was a creative act. Gas clouds slammed together, triggering bursts of star formation, while dark matter halos intertwined like tangled vines. Over billions of years, hundreds or even thousands of these mergers stacked up, layering stars and gas into the behemoths we recognize today. The Milky Way, for instance, likely grew from hundreds of these ancestral building blocks, devouring them like a cosmic puzzle assembling itself piece by piece. Here's what's astonishing: some of those primordial mini-galaxies still survive. Orbiting the Milky Way are faint, relic galaxies like Segway 1, so small and dim they were only discovered in the last 2 decades. These living fossils contain stars nearly as old as the universe itself, offering a snapshot of that ancient era when galaxies were just learning how to exist. They're proof that the grandest structures in the cosmos didn't spring up fully formed. They were painstakingly built, one merger at a time, from the humblest beginnings. Galaxies might seem eternal, frozen in their majestic spirals and glowing halos, but the truth is far more violent. They're cosmic predators devouring their neighbors in a slow-motion feast. This process, called galactic cannibalism, is how the largest galaxies in the universe grow to staggering sizes, and our own Milky Way is no exception. Right now, it's tearing apart a smaller galaxy called the Sagittarius Dwarf, stretching its stars into a glittering stream that wraps around our galactic home like a celestial serpent. The Sagittarius Dwarf didn't stand a chance. Roughly 10,000 times less massive than the Milky Way, it wandered too close billions of years ago, and gravity's relentless pull began to shred it apart. Imagine a spider ensnaring a fly, not with a quick kill, but by patiently unraveling it over eons. The smaller galaxies, stars, and dark matter are being siphoned away, some flung into the Milky Way's outer halo, others spiraling toward its core. Telescopes have mapped these stolen stars, tracing their paths like breadcrumbs leading back to the crime scene. But this isn't just destruction, it's transformation. Every time the Sagittarius Dwarf swings close to the Milky Way center, the tidal forces trigger bursts of star formation, igniting new suns from the chaos. The gas it once held now fuels the birth of future generations of stars, while its remaining structure warps into a twisted loop, destined to fade into the Milky Way's bulk. This isn't a rare event either. Astronomers have found at least a dozen such stellar streams around our galaxy, ghostly remnants of past meals. The Milky Way's appetite won't stop here. In about 4 billion years, it's set to collide with the even larger Andromeda galaxy, a merger that will reshape both into a single, colossal elliptical galaxy. Yet even that won't be the end. Smaller galaxies will continue to fall victim, their stars assimilated into an ever-growing galactic empire. It's a reminder that the universe operates on scales of both beauty and brutality, where the very forces that build galaxies also demand a constant sacrifice. At the heart of nearly every large galaxy, there's a monster waiting, a supermassive black hole, weighing millions or even billions of times more than our Sun. These cosmic giants aren't just passive occupants, they're active players in shaping the galaxies they call home. Take Sagittarius, a star, the black hole at the center of the Milky Way. While it seems quiet now, astronomers have found evidence of past eruptions so powerful they could have blown entire star systems apart. How do these invisible beasts influence galaxy formation? It starts with gravity. As a galaxy grows, gas and dust spiral inward, feeding the black hole. But here's the twist: when the black hole devours too much, it doesn't just swallow material quietly. It belches out colossal jets of energy, heating surrounding gas to millions of degrees and blasting it outward. This creates a cosmic tug of war. Gravity pulls matter in, while the black hole's outbursts push it away. The result, a balancing act that can either ignite star formation or snuff it out entirely. In some galaxies, this process goes haywire. Quasars, the brightest objects in the universe, are actually supermassive black holes in hyperactive feeding frenzies, their energy output outshining all the stars in their host galaxies combined. But these extreme outbursts have a purpose. By ejecting gas at incredible speeds, they can starve a galaxy of the raw materials needed to make new stars, effectively putting a cap on its growth. This might explain why the most massive galaxies in the universe often have fewer young stars. Their black holes have grown too powerful, regulating star formation like a cosmic thermostat. Yet not all black holes are destructive. Observations suggest that moderate activity from a central black hole can actually stimulate star birth in certain regions. Shockwaves from its outbursts might compress nearby gas clouds, triggering the collapse needed to form new stars. It's a delicate dance, too much energy, and the galaxy's gas is blown away, too little, and stars might form chaotically without regulation. The strangest part, we still don't fully understand how these supermassive black holes got so big so fast. Some appear fully formed when the universe was less than 1 billion years old, defying expectations. Did they grow from the collapse of early supermassive stars, or were they seeded by direct collapses of giant gas clouds in the infant cosmos? Whatever their origin, one thing's clear: galaxies and their central black holes grow together, locked in a feedback loop that shapes their evolution over billions of years. Without these gravitational titans, the universe's grandest structures might look entirely different, proof that even the darkest corners of space hold the keys to creation itself. Those graceful spiral arms stretching across galaxies like the Milky Way, they look like permanent fixtures, cosmic pinwheels frozen in motion. But here's the mind-bending truth: those arms aren't solid structures at all. They're an illusion, a stellar traffic jam where stars and gas pile up in waves that move through the galaxy like ripples on a pond. Picture a crowded highway where cars briefly cluster around an accident before speeding up again, except in this case, the cars are stars and the accident is a gravitational wave compressing everything in its path. This phenomenon, called a density wave, explains why spiral arms seem so vivid despite the fact that stars are constantly orbiting in and out of them. As gas clouds enter the wave, they squeeze together under the increased gravity, triggering bursts of star formation. The brightest, youngest stars light up the arms like street lamps along a cosmic boulevard, but they don't stay there forever. Over millions of years, these stars drift ahead or fall behind the wave, while new clouds of gas enter the cycle, feeding the next generation of stars. It's a self-renewing pattern, a celestial conveyor belt where the arms persist even as the stars that define them come and go. The proof is in the motion. If spiral arms were rigid structures, they'd wind themselves tighter and tighter as the galaxy rotates, eventually dissolving into chaos. Instead, they maintain their shape because the wave moves at a different speed than the stars and gas. Imagine a whip crack moving along its length. The wave travels, but the material it passes through stays in place. This delicate balance explains why some galaxies have kept their spiral patterns for billions of years, their arms constantly refreshed by fresh gas and newborn stars. What's even wilder, these density waves might be sparked by galactic collisions or the gravitational tug of neighboring galaxies, like a pebble dropped into a still pond. Some astronomers even suspect the Milky Way's own spiral structure was shaped by its repeated encounters with the Sagittarius Dwarf galaxy. Every time this tiny galaxy plunges through our galactic plane, it sends gravitational ripples through the disk, potentially reinforcing the spiral arms we see today. So the next time you gaze at a spiral galaxy, remember, you're not seeing a static sculpture, but a dynamic, ever-changing dance. The stars we admire in those luminous arms are just temporary passengers, caught in a wave that will eventually leave them behind, a wave that has been rolling through the cosmos since long before our sun ignited, and will continue long after it fades away. Elliptical galaxies are the cosmic equivalent of retired giants, once vibrant and star-forming, now quietly fading into old age. Unlike the flashy spirals with their star-studded arms, ellipticals are smooth, featureless spheres or ovals, glowing a dull red from the light of aging stars. But don't mistake their calm appearance for a peaceful history. These galaxies are the survivors of unimaginable violence, their serene shapes masking a past filled with collisions, mergers, and the brutal stripping away of their star-forming gas. The transformation begins when two spiral galaxies collide. Picture two cosmic whirlpools slamming together, their delicate arms shredded by gravitational forces. As their gas clouds smash into one another, the intense pressure triggers a firestorm of new star formation, what astronomers call a starburst. For a brief, brilliant moment, the merging galaxy outshines all others in its neighborhood. But this frenzy comes at a cost. The very gas that fuels the starburst is either used up in creating stars or blown away by the explosive energy of supernova and supermassive black holes. What's left is a galaxy that's red and dead, a term scientists use to describe ellipticals, where little to no new stars are born. Without fresh gas reserves, these galaxies become stellar graveyards. Their remaining stars age together, growing redder as they burn through their fuel, with no young blue stars to brighten the mix. Over billions of years, the orbits of their stars randomize, smoothing the galaxy into that classic elliptical shape. Unlike spirals, where stars move in orderly rotations, elliptical galaxies have stars darting in every direction like bees trapped in a jar. This chaos is another clue to their violent origins. Each major merger scrambles stellar orbits further, erasing any trace of their former structure. The scale of these mergers is staggering. The largest ellipticals, known as brightest cluster galaxies, sit at the hearts of galaxy clusters where they've grown by devouring smaller neighbors over eons. Some contain trillions of stars and weigh 100 times more than the Milky Way. These are the true titans of the universe, built through relentless cosmic cannibalism. And yet, despite their size, their futures are quiet. With no gas left to form new stars, they'll slowly dim over time, their stars burning out one by one until only cooling embers remain. But here's the twist: ellipticals aren't entirely dead. Recent observations reveal some still host reservoirs of hot gas, and a few even show signs of faint, late-life star formation. It's as if these retired giants occasionally stir from their slumber, drawing on whatever scant resources remain for one last burst of activity. Even in their twilight, they remind us that galaxies, like stars, have life cycles, and that the universe has a way of wringing beauty from even the most violent transformations. Galactic collisions defy everything we know about speed. When we imagine two galaxies smashing together, it's tempting to picture a cosmic car crash, a sudden, violent impact. But the reality is far slower, stretching across timescales so vast they're almost impossible to grasp. Take the impending collision between our Milky Way and the Andromeda galaxy. Right now, Andromeda is hurtling toward us at around 250,000 miles per hour. Yet even at that blistering speed, the merger won't truly begin for another 4 billion years. Why so slow? Galaxies are mostly empty space. Despite containing hundreds of billions of stars, the average distance between them is so enormous that direct stellar collisions are almost unheard of. Instead, this dance unfolds through gravity's invisible pull, a gradual wrapping and rewrapping of two immense structures. Picture two clouds of smoke drifting into one another. Their edges might touch first, swirling and distorting long before their cores ever meet. That's how galaxies merge, not with a bang, but with an eons-long embrace. The first signs will be subtle. As Andromeda approaches, its gravity will warp the Milky Way's outer disk, tugging stars into stretched-out tidal streams. Over millions of years, these tendrils of stars will arc across the sky, visible to any civilizations around to witness them. Then, the galaxies will make their first close pass, not a head-on crash, but a gravitational sidestep that sends both spiraling back toward each other in an ever-tightening orbit. Each pass will strip away more stars and gas, flinging some into intergalactic space while the rest eventually settle into a new, blended galaxy. What's astonishing is how gentle this violence can be. The gas clouds within both galaxies will slam together, triggering fireworks of new star formation, but the stars themselves, they'll mostly glide past one another, their paths bent but unchanged. Only the rare few will collide, and even then, the vast distances between the mean-most solar systems will emerge unscathed. By the time the merger completes roughly 6 billion years from now, the Milky Way and Andromeda will have transformed into a single, football-shaped elliptical galaxy, its once spiral arms erased by the gravitational chaos. Yet for all the drama, the night sky will still be full of stars, just arranged in new, unfamiliar patterns. It's a reminder that even the most cataclysmic events in the universe unfold at a pace we can barely fathom, sculpting the cosmos one slow, graceful step at a time. Some galaxies don't just form stars, they explode with them, birthing and destroying suns at a rate that defies imagination. Take the Cigar Galaxy, officially known as Messier 82, a fiery slash of light in the constellation Ursa Major. At first glance, it might look like a typical spiral galaxy seen edge-on, but peer closer, and you'll discover a cosmic riot in progress. Here, stars aren't just born, they erupt into existence at a pace 10 times faster than in our own Milky Way, igniting so furiously that the galaxy practically vibrates with energy. What triggers this stellar frenzy? The answer lies in gravitational trauma. Millions of years ago, M82 had a close encounter with its massive neighbor, Messier 81. The gravitational tug of war between the two galaxies sent shockwaves through M82's gas clouds, compressing them until they collapsed under their own weight. Like a snowball rolling downhill, this process fed on itself. Each new generation of stars exploded as supernova, their shockwaves triggering even more star formation in a runaway chain reaction. The result, a galaxy-wide fireworks show where supernova detonate every few decades, compared to the Milky Way's relatively sedate rate of 1 or 2 per century. The consequences are breathtaking. Massive stars burn bright and die young, their short lives ending in explosions so powerful they hurl material clear out of the galaxy. Telescopes reveal colossal plumes of gas stretching tens of thousands of light-years into space, a testament to the violence within. Meanwhile, the galaxy's core churns with activity, its central regions glowing from the combined light of millions of young, hot stars packed so tightly they outshine entire normal galaxies. It's as if nature took the rulebook for galactic evolution and tossed it aside, opting for chaos instead of order. Yet even this frenzy has limits. Starburst galaxies like M82 are cosmic mayflies, brilliant but brief. Their gas reservoirs, depleted by reckless star formation, will eventually run dry. Without fresh fuel, the fireworks will sputter out, leaving behind a galaxy littered with the remnants of its explosive youth, neutron stars, black holes, and aging stellar populations. For now, though, M82 stands as a dazzling reminder of how a single gravitational nudge can turn an ordinary galaxy into a supernova factory, proving that even in the vast, cold expanse of space, things can get very, very hot. Edwin Hubble's famous classification system, the Hubble sequence, gave us a way to organize galaxies into neat categories: spirals with their winding arms, ellipticals like smooth cosmic eggs, and irregulars defying any clear shape. For decades, this system shaped how we understood galactic diversity. But here's the catch: the universe doesn't play by our rules. The more we've observed, the clearer it becomes that galaxies refuse to fit into tidy boxes. Some spiral galaxies have bars cutting through their centers like cosmic highways. Others, like the rare ring galaxies, look like stellar bullseyes, their stars arranged in perfect circles from ancient collisions. Then there are lenticular galaxies, neither spiral nor elliptical, but something in between, like celestial frozen whirlpools. Hubble's system also misses the drama of galactic transformation. A spiral galaxy doesn't wake up one day and decide to become an elliptical. The change happens over billions of years through mergers, gas depletion, or black hole activity, leaving many galaxies in transitional states that defy classification. Take the jellyfish galaxies, their gas stripped away by the brutal forces of galaxy clusters, trailing tendrils of star formation like cosmic tentacles. Or tadpole galaxies with bright heads and long, starry tails, caught mid-distortion after a close encounter. These oddballs aren't exceptions, they're proof that galaxies are constantly evolving, often in ways Hubble never anticipated. Even the shapes we think we know hide surprises. Not all spirals are created equal. Some have arms so faint they're barely there, while others, like grand design spirals, boast arms so sharp they look drawn by a cosmic architect. Ellipticals, often dismissed as featureless, can have hidden structures, shells of stars layered like onion skins from past mergers, or faint disks lurking beneath their smooth exteriors. And irregular galaxies, they're not just chaotic leftovers. Some, like the large Magellanic Cloud, are bustling with star-forming regions, their apparent disorder hiding intricate balances of gravity and motion. The Hubble sequence was a brilliant first step, but it's like sorting animals into birds, fish, and mammals, while ignoring the platypus. Modern astronomy reveals galaxies as dynamic, ever-changing entities, each with its own story. Some are hybrids, some are caught mid-transformation, and others challenge our definitions entirely. The universe doesn't do simplicity, it thrives on diversity, and every time we think we've mapped its boundaries, galaxies remind us how much more there is to discover. Galaxies don't just grow, they bleed. Across the cosmos, colossal winds of superheated gas stream outward from galactic centers, propelled by the combined fury of supernova and supermassive black holes. These aren't gentle breezes, they're million-mile-per-hour tempests powerful enough to strip galaxies of the very material they need to birth new stars. Imagine a farmer scattering seeds, only for a hurricane to rip them away before they can take root. That's the cruel irony of galactic winds. They're born from the same stellar explosions that create the heavy elements needed for life, yet they also starve galaxies of their future. Take the nearby galaxy Messier 82, a starburst powerhouse where stars explode 100 times more frequently than in our Milky Way. Each supernova acts like a cosmic pressure washer, blasting gas outward in shockwaves that collide, merge, and eventually erupt into space as a unified wind. Hubble Space Telescope observations reveal these outflows stretching tens of thousands of light-years, far beyond the galaxy's visible edges, carrying enough material to build millions of new stars. But here's the catch: once that gas escapes gravity's grip, it's lost forever, drifting into the lonely voids between galaxies, and it's not just supernova doing the damage. At the heart of many galaxies, supermassive black holes contribute their own apocalyptic gusts. When these monsters feed, they don't just swallow matter quietly, they belch out energy in the form of relativistic jets and radiation, heating surrounding gas until it glows white-hot and flees the galaxy. The Phoenix Cluster's central galaxy, for instance, hosts a black hole so voracious its winds have created vast bubbles in the surrounding hot gas, each large enough to swallow our entire solar system thousands of times over. These winds aren't just destructive, they're regulators. By ejecting gas, they put a brake on runaway star formation, preventing galaxies from growing too big too fast. In massive galaxies, this feedback loop explains why star formation often peaks early, then dwindles. The same winds that once seeded the cosmos with heavy elements eventually turn off the tap, leaving galaxies to age in quiet solitude. Yet some gas resists. Dense clouds shielded by dust or magnetic fields can cling to the galaxy like survivors of a storm. Over eons, this gas might cool and fall back, seeding pockets of late-life star formation. It's a fragile balance: too much wind, and the galaxy dies young; too little, and it burns out in a frenzy of unchecked star birth. This interplay between creation and destruction is woven into every galaxy's story, a reminder that even the grandest cosmic structures are shaped by forces they can't contain. Deep in the Milky Way's core lies a relic from the dawn of time, a dense, ancient swarm of stars that witnessed the universe in its infancy. This galactic bulge, a football-shaped cloud of stellar elders, contains stars dating back over 13 billion years, making them some of the first to ignite after the Big Bang. Unlike the younger, metal-rich stars of the spiral arms, these primordial suns are composed almost entirely of hydrogen and helium, the raw materials of the early cosmos. They burn faintly now, their light dimmed by eons, but their existence tells a story of a time when the Milky Way was just a fledgling gathering of gas and dark matter. Studying these stars is like cracking open a cosmic time capsule. Their composition holds clues to conditions in the universe's first billion years before supernova had seeded space with heavier elements. Some bulge stars have so little metal content that astronomers jokingly call them pristine, barely altered since their birth. Their orbits, too, reveal secrets. Unlike the orderly rotations of younger stars in the galactic disk, these ancient suns move in chaotic, plunging trajectories, a sign they were born before the Milky Way settled into its elegant spiral structure. But how did they survive so long in such a tumultuous environment? The bulge is one of the most crowded and violent regions of the galaxy, where stars are packed so tightly they nearly brush against one another, and the supermassive black hole Sagittarius, a star, lurks at the center, capable of flinging stars into deep space with its gravity. The answer lies in simplicity. These stars are small, dim, and incredibly tough. Red dwarfs, the most common type in the bulge, burn so slowly they'll outlive the universe itself, while ancient giants have already weathered billions of years of cosmic chaos. What's truly astonishing is that we can see them at all. Peering through the galactic dust that shrouds the bulge requires infrared telescopes like the James Webb Space Telescope, which can detect the heat signatures of these faint, old stars. Each one we uncover adds another piece to the puzzle of how galaxies like ours emerged from the primordial darkness. They're living fossils, remnants of an era when the Milky Way was just a whisper of what it would become, and proof that even in the universe's busiest neighborhoods, the past is still written in starlight. Galaxies aren't supposed to die young, yet some do, their star-making factories shutting down in what astronomers call quenching. Imagine a thriving metropolis where every construction site suddenly goes silent, cranes frozen in place, raw materials left unused. That's what happens when a galaxy quenches. Its gas supply, the lifeblood of star formation, is either snatched away or heated beyond use, leaving a galaxy full of aging stars with no new generations to replace them. One of the biggest culprits, supermassive black holes. When these monsters at galactic centers feast on too much material, they don't just eat quietly, they spew out torrents of energy in the form of jets and radiation. These outbursts can heat surrounding gas to millions of degrees, making it too energetic to collapse into new stars. It's like trying to build a snowman during a heat wave. The material is there, but conditions won't let it stick together. In extreme cases, these black hole winds blast gas clean out of the galaxy, starving it permanently. Some of the universe's most massive elliptical galaxies likely met their end this way, their star-forming potential snuffed out by the very engines at their hearts. But black holes aren't the only force at work. For galaxies in crowded clusters, a sinister environmental effect called ram pressure stripping can tear away their gas. Picture a galaxy cruising through a cluster's hot intergalactic medium. The friction is like sticking your hand out a car window at highway speeds. The pressure rips gas away, leaving the galaxy with nothing to fuel new stars. The Virgo cluster's spiral galaxies show this brutally. Many have long, ghostly tails of stripped gas trailing behind them, evidence of their slow-motion dismantling. There's a cruel irony here. The same violent processes that create stars' supernova explosions can also trigger quenching when they become too intense. In starburst galaxies where stars form at breakneck speeds, supernova can collectively blast gas out like a cosmic pressure washer, leaving behind a galaxy that burned brightly but briefly. It's a galactic cautionary tale. Too much of a good thing can lead to an early demise, yet some galaxies resist. Deep in their cores, pockets of dense, cool gas can survive these onslaughts, hiding like seeds waiting for better times. Astronomers have even found rejuvenated galaxies where fresh gas, perhaps snatched from a neighbor or siphoned from intergalactic filaments, reignites star formation after billions of years of silence. It's proof that even in the cosmos, second chances exist if conditions are just right. The universe isn't just a random scattering of galaxies, it's a vast, intricate web, with galaxies strung along invisible threads like beads on a necklace. These filaments, made of dark matter and hydrogen gas, stretch across billions of light years, weaving the largest structure known to science, the cosmic web. Picture a spider's silk, but on a scale so immense that entire galaxy clusters dangle at the intersections where strands cross. This isn't just a pretty pattern, it's the backbone of cosmic growth, the delivery system that feeds galaxies the raw materials they need to thrive. At the dawn of time, gravity began sculpting this web from the faintest ripples in the infant universe. Dark matter, unaffected by light or pressure, clumped first, forming a scaffolding of tendrils. Ordinary gas, pulled by gravity's invisible hand, flowed into these channels, pooling at the intersections. Over billions of years, these dense knots became the birthplaces of galaxies, while the filaments themselves acted as pipelines, funneling fresh hydrogen fuel to hungry galaxies along their length. Even now, the Milky Way sits within a filament, drawing gas from this colossal network like a tree tapping into underground streams. The proof of this structure is etched across the sky. Massive galaxy surveys reveal galaxies lining up along these filaments, their positions tracing out the web's skeleton. Between them lie the voids, enormous, nearly empty deserts of space where galaxies are rare and lonely. The contrast is staggering. Filaments host thousands of galaxies per cubic light year, while voids may have just one or two. This isn't random chance, it's gravity's handiwork, a cosmic sorting mechanism that concentrates matter where the threads are tightest. But here's the twist. The cosmic web isn't static. Gas still flows along these filaments, pulled toward galaxy clusters by gravity's unrelenting tug. Telescopes have caught this process in action, spotting distant galaxies with elongated gas tails, evidence of them drinking from the web streams. Some galaxies, positioned near filament intersections, grow fat on this steady diet, while others, stranded in the voids, starve for lack of fresh material. The web's influence doesn't stop at feeding galaxies, it also shapes their destinies. Galaxies nearer to filaments tend to mature faster, their gas supply rich and constant, while those farther away evolve more slowly. Even the Milky Way's history, its periods of rapid star formation followed by quiet spells, may be tied to the ebb and flow of gas through our local filament. In this way, the cosmic web isn't just a backdrop, it's a dynamic force quietly guiding the growth of every galaxy within its grasp. What's astonishing is how fragile this system can be. The filaments, though massive, are easily disrupted by the very galaxies they feed. Supernova explosions and black hole outbursts can blow holes in the nearby web, altering the flow of gas for millions of light years around. It's a delicate balance. The web builds galaxies, and galaxies, in turn, reshape the web. This feedback loop has been running since the first galaxies flickered to life, and it will continue until the last stars fade, a reminder that even the grandest structures in the cosmos are part of an endless cycle of giving and taking. For every majestic spiral galaxy like the Milky Way, there are hundreds, perhaps thousands of tiny, unassuming dwarfs lurking in the cosmic shadows. These diminutive galaxies, some no larger than a globular cluster, are the universe's silent majority, outnumbering their giant counterparts by an astonishing margin. Yet despite their abundance, many remain hidden, their faint glow drowned out by the brilliance of nearby stars or the glare of larger galaxies. It's like trying to spot fireflies next to a spotlight. The universe's grandest structures have been stealing the show, while the true galactic population humbly fades into the background. What makes dwarf galaxies so common? The answer lies in the early universe, where dark matter's gravitational pull sculpted the first clumps of gas into countless small halos rather than a few massive ones. Picture a rainstorm filling puddles. While some grow large, most remain small and scattered. These primordial dwarfs were the building blocks of today's giants, but many never merged, surviving as relics of that ancient era. The Milky Way's own satellite galaxies, like the large and small Magellanic clouds, are just the tip of the iceberg. Telescopes have uncovered dozens more orbiting our galaxy, each a faint smudge of stars holding clues to the cosmos's formative years. Finding them isn't easy. Some dwarfs contain as few as 1,000 stars, spread so thin they blend seamlessly into the darkness. Others are so dominated by dark matter that their starlight barely registers. Take Segway 1, one of the faintest galaxies ever detected. Its total brightness is less than 300 times that of our Sun, yet it weighs millions of times more due to unseen dark matter. Discovering these ghosts requires painstaking surveys, often using specialized telescopes to filter out foreground stars or detect the subtle ripples they create in the cosmic microwave background. But their modesty hides cosmic significance. Dwarf galaxies are time capsules preserving conditions from the universe's youth. Many lack heavy elements, their stars forged from pristine hydrogen and helium, untouched by the chemical enrichment of later generations. Their simple chemistry offers a window into an era before supernova seeded the cosmos with metals. Some even harbor intermediate black holes, rare middleweights that could hold clues to how supermassive black holes first formed. The sheer number of undiscovered dwarfs hints at secrets still waiting in the darkness. Simulations suggest thousands might orbit the Milky Way, their faint signals lost in the noise. Future telescopes like the Vera Rubin Observatory aim to uncover them, mapping the full scope of our galactic neighborhood. Every new discovery reshapes our understanding of galaxy formation, proving that sometimes the universe's most important stories are told not by its giants but by its quietest whispers. Galaxies might seem like one-way systems flinging gas into space through supernova and black hole winds, never to return, but the universe has a way of recycling. Enter galactic fountains, nature's cosmic recycling program where expelled gas doesn't just vanish. It arcs back like water in a celestial fountain, raining down to fuel new generations of stars. Picture a geyser on an unimaginable scale. Supernova explosions blast gas hundreds of thousands of light years upward, where it cools, condenses, and eventually plummets back, seeding the galaxy with fresh star-forming material. This process is messy, violent, and breathtakingly efficient. When massive stars explode, their shockwaves heat surrounding gas to millions of degrees, launching it out of the galactic disk at blistering speeds. But unlike the gas lost to intergalactic space forever, some of this material gets caught in a delicate balancing act. As it rises, the gas expands and cools, mixing with denser pockets of colder material in the galaxy's halo. Over millions of years, gravity's pull overcomes the outward momentum, dragging these now heavy clouds back toward the disk. The result, a slow-motion downpour of revitalized gas, landing far from its origin like cosmic rainfall. One of the best-studied examples lies right in our cosmic backyard, the Milky Way's own Fermi bubbles. These towering structures, stretching 25,000 light-years above and below the galactic center, are remnants of an ancient outburst likely caused by our supermassive black hole. While their edges bleed gas into intergalactic space, the inner regions show something remarkable: filaments of cooler gas condensing and falling back, like mist settling after a storm. Observations from the Hubble Space Telescope reveal these returning streams are rich in heavy elements, the ashes of long-dead stars now repurposed to build new ones. But galactic fountains aren't just about recycling their regulators. By controlling how much gas escapes versus how much returns, they fine-tune a galaxy's star-forming efficiency. Too much outflow and the galaxy starves, too little, and it might overheat or exhaust its fuel too quickly. Some galaxies, like Andromeda, show evidence of multiple fountain cycles layered over eons, each pulse of outflow and return leaving its mark in the chemical makeup of succeeding stellar generations. It's a self-correcting system, ensuring galaxies don't burn too bright and fast or fade too soon. The most surprising twist: these fountains might explain why some galaxies avoid quenching, that premature shutdown of star formation. Even as black holes and supernova blast gas away, the fountain's return flow provides a lifeline, a way to keep the star-making factories running on recycled material. In a universe where nothing truly goes to waste, even the most violent explosions have a role to play in the endless cycle of creation and renewal. So the next time you gaze at a star-filled sky, remember, some of those twinkling lights were forged from the ashes of their ancestors, brought back to life by gravity's patient hand. Galaxy clusters are cosmic pressure cookers, environments so harsh they can strip away a galaxy's identity, turning elegant spirals into bland, featureless ellipticals. This dramatic transformation, known as the Butcher-Ohmler effect, was first spotted in the late 1970s when astronomers noticed something odd about distant galaxy clusters. They contained far more blue, star-forming spirals than nearby clusters, which were dominated by red, dead ellipticals. The implication was staggering. Clusters weren't born this way. They evolved, systematically converting their vibrant members into aging relics over billions of years. The mechanism behind this metamorphosis is as brutal as it is efficient. When a spiral galaxy falls into a dense cluster, it's hit by a 1-2 punch of environmental violence. First comes ram pressure, stripping the intergalactic equivalent of sticking your hand out a speeding car window. The cluster's hot, thin gas rams into the galaxy's own gas reservoirs, ripping them away like tissue paper in a hurricane. Without fresh fuel, star formation grinds to a halt, and the galaxy's distinctive spiral arms fade as its brightest young stars die off. But the abuse doesn't stop there. Gravitational tides from the cluster's monstrous central galaxy and dark matter halo twist and stretch the newcomer, pulling stars from its outer edges into long, ghostly streams. Over time, repeated close encounters with other cluster members, a phenomenon called harassment, randomize the galaxy's stellar orbits, smoothing its once crisp spiral structure into the shapeless blur of an elliptical. The process isn't quick. It can take billions of years, but the end result is irreversible. The galaxy, once a vibrant, star-making machine, becomes just another red and dead fossil in the cluster's graveyard. What's truly fascinating is how this effect scales with distance and thus time. Peering at faraway clusters means looking into the past, and the Butcher-Ohmler effect reveals clusters were once lively places, teeming with blue spirals actively forming stars. As the universe aged, these bustling galactic cities grew quieter, their populations homogenized by relentless environmental pressures. Even our own Milky Way, if it were plunged into a dense cluster like Coma, would suffer the same fate: its gas stripped, its arms unraveled, its star-forming potential snuffed out. But here's the twist: not all spirals go quietly. Some resist complete transformation, clinging to patches of gas that allow sporadic star birth. Others, like the so-called jellyfish galaxies, trail tales of stolen material, evidence of their struggle against the cluster's grip. These holdouts prove that while the Butcher-Ohmler effect may be inevitable in the long run, galaxies don't surrender their identities without a fight. It's a reminder that the universe isn't just a place of creation. It's also a realm of slow, inexorable change, where even the grandest structures are shaped by forces beyond their control. Some galaxies break all the rules by dying before their time, collapsing into stellar retirement when the universe was barely out of its infancy. Astronomers peering back over 12 billion years have made a startling discovery: massive galaxies fully formed and then mysteriously quenched, their star formation snuffed out when the cosmos was less than a fifth of its current age. These cosmic anomalies, like the galaxy ZF Cosmos 20115 found in 2012, weigh as much as the Milky Way but are filled with aging red stars, their blue spark of youth long extinguished. The existence of such galaxies throws our understanding of cosmic evolution into chaos. How could something so massive form so early? And what catastrophic force could have shut down its star factories almost immediately? The timeline doesn't add up. Current models suggest it should take billions of years for a galaxy to grow this large and then exhaust its gas supply. Yet here are these ancient behemoths already red and dead when the universe was just 1 billion years old, like finding the ruins of a skyscraper in the middle of the Stone Age. Their sheer size hints at an era of hyper-efficient star formation, where gas converted into stars at rates hundreds of times faster than in modern galaxies. Imagine a wildfire raging through a forest so intensely that it burns itself out in minutes, leaving only embers behind. That's how abruptly these galaxies seem to have lived and died. But what could trigger such a rapid shutdown? One leading theory points to their supermassive black holes going rogue. In the early universe's dense, chaotic environment, black holes may have gorged themselves on gas, then spewed out enough energy to blast away or overheat their galaxy's remaining fuel. The evidence lies in distant quasars, extremely luminous black holes whose energy output could have sterilized entire galaxies in just a few million years. Another possibility is that these galaxies formed in unusually dense regions where collisions stripped away their gas, like trees in a hurricane losing their leaves all at once. The most baffling examples are the red nuggets, compact, dead galaxies so dense they pack a Milky Way's worth of stars into a space 20 times smaller. These cosmic prunes seem to defy physics, having somehow resisted the mergers that typically puff galaxies up over time. Some may have been the dense cores of larger galaxies that had their outer layers shredded, leaving only their tough, impenetrable hearts behind. Others might represent a lost generation of galaxies that formed through a now extinct process, their secrets buried in starlight older than Earth itself. What's truly unsettling is that these early dead galaxies aren't rare oddities, they're shockingly common. Recent surveys suggest up to half of all massive galaxies in the early universe were already dead when the cosmos was just 3 billion years old. This implies an entire hidden chapter of galactic history, one where the rules of formation and quenching worked differently than they do today. Every new discovery peels back another layer, revealing a universe far more dynamic and unpredictable than we ever imagined, where galaxies could rise to glory and fade into darkness before the cosmic dawn had fully broken. Magnetic fields might be invisible, but their influence on galaxies is anything but subtle. These vast cosmic force fields thread through galaxies like unseen spiderwebs, shaping the flow of gas and dust on scales so immense they defy comprehension. While gravity gets all the attention for sculpting galaxies, magnetism works behind the scenes, guiding, compressing, and sometimes even halting the very processes that give birth to stars. Picture a river diverted by an unseen hand, its currents twisting in unexpected ways. That's how magnetic fields operate within the interstellar medium, steering the raw materials of star formation with ghostly precision. Take the spiral arms of galaxies like our Milky Way. While gravity creates the broad strokes of these structures, magnetic fields add the fine details. Observations from radio telescopes reveal that these arms aren't just dense with gas, they're laced with magnetic fields strong enough to align dust grains like microscopic compass needles. As gas clouds move through these magnetized regions, the fields act like cosmic traffic cops, channeling turbulent flows into orderly streams. This organization is crucial. Without it, gas might disperse too chaotically to ever collapse into stars. Some studies even suggest that in certain galaxies, magnetic pressure can rival gravity itself, becoming the dominant force in shaping how interstellar material moves and clusters. But magnetism's role isn't always constructive. In some environments, these fields become galactic gatekeepers, preventing star formation rather than enabling it. When gas clouds become too magnetized, the fields can resist compression, like an invisible spring pushing back against collapse. This might explain why some galaxies, particularly older ellipticals, have mysteriously stopped forming stars despite having plenty of gas. The gas is there, but it's magnetically locked, unable to condense past a critical threshold. It's a cosmic irony. The same force that helps create stars in one galaxy can strangle their birth in another. The most dramatic effects occur around supermassive black holes. Here, magnetic fields don't just influence gas, they choreograph entire plasma ballets. Near the Milky Way's core, astronomers have detected magnetic filaments stretching dozens of light years, their structure so precise they look almost engineered. These filaments channel gas toward the black hole while simultaneously launching jets of material outward at nearly light speed. Without magnetic fields to focus these outflows, galaxies might lose their gas too quickly, starving future generations of stars before they ever ignite. What's truly astonishing is how these fields originate. Unlike bar magnets with clear north and south poles, galactic magnetic fields emerge from chaos. Turbulence in ionized gas, stirred by supernova explosions and stellar winds, twists and amplifies weak seed fields until they become galaxy-spanning networks. It's a self-perpetuating cycle. The fields shape star formation, and the stars, in turn, reinforce the fields through their explosive deaths. We're only beginning to map this hidden architecture. New instruments like the Square Kilometer Array radio telescope promise to reveal magnetic structures in unprecedented detail, showing how they weave through galaxies both near and far. Already, we've learned that no two galactic magnetic fields are alike. Some spiral neatly with their host galaxy's arms, others tangle like dropped yarn, and a few even flip polarity on scales larger than our solar system. This diversity hints at an underlying order we're just starting to decipher, a reminder that even in the vast emptiness of space, invisible forces are always at work, quietly guiding the birth and evolution of galactic landscapes. The universe has a dark matter mystery on its hands, one that lurks right in our galactic backyard. According to our best simulations, the Milky Way should be swarmed by thousands of dwarf galaxies, tiny satellites held in orbit by vast cocoons of dark matter. But when astronomers actually count them, the numbers don't add up. We've only spotted about 60 so far, leaving a glaring gap between prediction and reality that's become one of cosmology's most stubborn puzzles, the missing satellite problem. This isn't just about missing galactic specks, it strikes at the heart of our understanding of dark matter itself. Supercomputer models of cosmic structure formation paint a vivid picture. As the Milky Way grew, it should have pulled in countless small dark matter halos, each potentially cradling enough gas to form a dwarf galaxy. The math suggests there ought to be 10 times as many as we see. So where did they all go? One possibility is that most dwarfs never got the chance to shine. Dark matter halos may have formed in droves, but if the early universe's fierce radiation stripped away their gas before stars could ignite, they'd remain invisible, dark matter ghosts with no stellar light to betray their presence. Telescopes like the upcoming Vera Rubin Observatory aim to find these dark galaxies by spotting the rare stars they might have managed to form, or by detecting distorted starlight as their gravity lenses background objects. Another twist comes from the dwarfs. We can see they're arranged oddly. Instead of clustering randomly around the Milky Way, many orbit in a single, vast plane, like flies trapped on a windowpane. This suggests they might be ancient debris from a single, larger galaxy torn apart long ago, rather than independent systems. If true, it implies that mergers play a bigger role in dwarf populations than we thought, potentially explaining some of the missing numbers. The most radical solution, maybe dark matter isn't what we think. Alternative theories like warm dark matter that moves faster than the traditional cold variety could produce fewer small halos naturally. Or perhaps dark matter interacts with itself in ways that erase smaller structures over time. Every undiscovered dwarf galaxy is a clue, and every new observation tightens the noose around this cosmic whodunit. What's clear is that these missing satellites aren't just gaps in a map, they're signposts pointing to physics we don't yet understand. Whether the answer lies in galaxy formation, dark matter's nature, or something even stranger, solving this puzzle could rewrite the rules of the cosmos. Until then, the silent majority of the Milky Way's companions remain hidden, a reminder that even in our own corner of the universe, the simplest questions can have the most profound implications. Some galaxies don't just drift through space alone, they waltz. Take the antennae galaxies, two spirals locked in a gravitational embrace so intimate it stretched them into celestial artworks. Named for their long, antenna-like tidal tails, these galaxies are mid-collision, their spiral arms unraveled into luminous streamers that glow with the birth of millions of new stars. What makes this dance so mesmerizing isn't just the spectacle, it's the physics. As the galaxies swing past each other, their mutual gravity tugs fiercely on stars and gas, flinging some into deep space while compressing others into dense knots. These compressed regions ignite star formation at a rate hundreds of times faster than in isolated galaxies, turning the antennae into a cosmic fireworks display. The dance began roughly 300 million years ago, a blink in cosmic time when these galaxies first brushed against each other. Now they're so entangled it's hard to tell where one ends and the other begins. Their cores, each harboring a supermassive black hole, are circling closer with each pass, destined to merge into a single, even larger black hole. Meanwhile, their tidal tails, each stretching hundreds of thousands of light years, are studded with superstar clusters, some weighing as much as 1 million suns. These clusters are the universe's way of recycling chaos into creation, forging new stellar generations from the wreckage of the old, but the antennae aren't unique. Across the universe, galactic dances play out in slow motion. The mice galaxies, for instance, are connected by a bridge of stars pulled from their bodies like taffy, while the whirlpool galaxy's graceful arms are distorted by the gravitational tug of a smaller companion. Each interaction follows the same script: gravity stretches, compresses, and reshapes, but rarely destroys. Even as galaxies tear each other apart, they're building something new, proof that in the cosmos, destruction and creation are two sides of the same coin. What's astonishing is how these collisions defy intuition. We might expect galaxies to shatter like glass when they meet, but they're mostly empty space. Stars are so far apart that direct collisions are rare. Instead, it's the gas between them that suffers the worst of it, shockwaves triggering stellar baby booms that light up the darkness. Over billions of years, these dancing partners will settle into a single, larger galaxy, perhaps an elliptical, its once elegant spirals erased by the frenzy of the merger. The antennae offer a glimpse of our own galaxy's future. When the Milky Way and Andromeda collide, they too will stretch into tidal tails, their cores swirling toward an inevitable union. But unlike the antennae, we won't just be observers, we'll be inside the dance, surrounded by skies reshaped by gravity's relentless pull. It's a reminder that even the grandest galaxies aren't islands, they're partners in an endless celestial ballet, choreographed by forces older than time itself. The sun doesn't sit still in the Milky Way, it sweeps through our galaxy's spiral arms in a grand, slow-motion arc, carrying Earth and every planet along for the ride. One complete orbit takes roughly 230 million years, meaning since our solar system formed 4.5 billion years ago, we've circled the galactic center about 20 times. Think about that. The last time we were in this exact spot, dinosaurs were just beginning their reign on Earth and flowering plants hadn't even evolved yet. This cosmic journey isn't a perfect circle, it's more like a gentle wave, bobbing up and down through the galactic plane as we go. As the Sun orbits, it weaves between the Milky Way's spiral arms, passing through regions dense with star-forming gas and others nearly empty. Each crossing leaves a subtle imprint. Some scientists speculate these periodic encounters might trigger comet showers in the outer solar system or even influence Earth's climate over eons. Our speed is staggering. The Sun hurtles through space at around 515,000 miles per hour relative to the galaxy's center. Yet because the Milky Way is so vast, this breakneck pace feels glacial, like a speck of dust caught in a slow-moving whirlpool. And we're not alone in this dance. Every star in our neighborhood follows a similar path, each with slight variations that create a swirling, dynamic flow. Here's what's wild. The Milky Way itself isn't static. It rotates like a giant pinwheel, with stars closer to the center completing orbits faster than those farther out. This differential rotation means spiral arms aren't fixed structures but density waves, regions where stars pile up temporarily, like cars in a cosmic traffic jam. Our solar system has drifted in and out of these arms countless times, each passage leaving no trace on our familiar night sky but potentially shaping the deep history of life on Earth. The most recent time we crossed a major spiral arm, the Orion Arm's outer edge, was roughly 50 million years ago, around the time mammals began their rise after the dinosaurs' extinction. Some theories suggest these crossings could expose Earth to higher cosmic radiation or gravitational nudges from nearby stars, though evidence remains elusive. What's certain is that our galactic orbit ties the solar system's fate to the Milky Way's grand structure, a reminder that even in the vastness of space, nothing truly travels alone. And the next lap, we're currently cruising through a relatively quiet patch between arms, a cosmic suburbs of sorts. In another 30 million years or so, we'll approach the next spiral arm, though by then the Sun will be slightly brighter, Earth may be unrecognizable, and any civilizations watching will witness a very different sky. For now, we're along for the ride, a tiny part of the Milky Way's slow, elegant turn through the cosmos. Peering into a galaxy isn't just about seeing its present, it's like cracking open a cosmic history book written in starlight. Every star holds clues, its chemical composition and motion telling stories of ancient mergers, violent births, and quiet evolutions. Astronomers call this galactic archaeology, and it's transforming how we understand the lives of galaxies, one stellar fossil at a time. Take the Milky Way. Our galaxy is a layered relic, its stars sorted by age like rings in a tree trunk. The oldest stars, those over 10 billion years, cluster in the galactic bulge and halo, their metal-poor composition betraying their origins in the universe's infancy. These ancient suns formed before supernova had seeded space with heavy elements, making them pristine time capsules. Their wild, looping orbits hint at a chaotic past when the Milky Way was just a jumble of gas and dark matter, not the elegant spiral we know today. Younger stars, rich in metals like iron and carbon, trace orderly paths in the disk, their chemistry revealing generations of stellar life and death that enrich the galaxy's raw materials. But galactic archaeologists don't just study individual stars, they read the broader patterns. Streams of stars arcing through the halo, like the remnants of the Gaia-Enceladus galaxy devoured by the Milky Way 8 to 10 billion years ago, are the fingerprints of ancient collisions. These stellar rivers, discovered by tracking the motions of millions of stars with telescopes like Gaia, show how galaxies grow by consuming smaller neighbors. Even our sun might be an immigrant. Its unusual mix of elements suggests it formed in a different region of the galaxy before migrating to its current orbit. The tools of this cosmic detective work are as precise as they are powerful. Spectrographs dissect starlight to reveal elemental abundances, while astroseismology measures stellar vibrations to determine ages, much like geologists date rocks. Combine this with 3D velocity maps and suddenly, stars become dynamic storytellers. For instance, the Milky Way's thick disk, a population of stars with slightly eccentric orbits, tells of a long-ago merger that stirred the galactic pot, scattering stars like flour tossed into dough. Beyond our galaxy, the same principles apply. In Andromeda, astronomers have identified stellar remnants of a colossal collision 2 billion years ago, its aftermath still visible in the motions of billions of stars. Dwarf galaxies like Segway 1, barely more than a star cluster, preserve the chemical signatures of the universe's first stellar generations, offering glimpses into how galaxies were built from the smallest fragments. What's astonishing is how recently this field has exploded. 20 years ago, we saw galaxies as static snapshots. Now, thanks to galactic archaeology, their dynamic biographies, their histories etched in the orbits and chemistry of their stars. Every new survey, like the upcoming Vera Rubin Observatory's 10-year scan of the sky, promises to uncover more chapters: lost galaxies absorbed by ours, periods of violent star formation, and perhaps even stars from other galaxies passing through like interstellar tourists. The ultimate goal: to piece together not just our galaxy's story, but the universal laws that shaped all galaxies. By comparing stellar fossils across the cosmos, we're learning why some galaxies die young while others thrive, how dark matter guides their growth, and what our own galactic neighborhood might look like in another billion years. It's a reminder that every star is more than a point of light. It's a witness to the past, carrying secrets of the cosmos in its glow. Somewhere beyond the stars, in the depths of intergalactic space, an invisible force tugs at our galaxy with irresistible strength. The Milky Way isn't floating aimlessly. It's racing toward an enigmatic region called the Great Attractor at a staggering 14 million miles per hour, dragging the entire local group of galaxies along with it. This cosmic phantom, hidden behind the thick dust of our own galaxy's disk, is one of the universe's most perplexing mysteries, a gravitational anomaly so powerful it defies easy explanation. For decades, astronomers were baffled by the peculiar motion of our galaxy. Even after accounting for the expansion of the universe, something was pulling us off course. The culprit, a concentration of mass equivalent to tens of thousands of Milky Ways, lurking about 250 million light-years away in the direction of the constellation Centaurus. But here's the twist: we can't actually see most of it. The Great Attractor lies in what's called the zone of avoidance, a region obscured by the Milky Way's own bright stars and dense gas clouds. It's like trying to spot a mountain through fog. We know it's there by its effects, but the details remain frustratingly blurred. What makes this cosmic tug-of-war even stranger is the Great Attractor's place in the larger cosmic web. It turns out this gravitational behemoth isn't the end of the journey. It's just a waypoint. Beyond it lies something even more colossal: the Shapley supercluster, a sprawling metropolis of galaxies containing more mass than 10,000 Milky Ways. This supercluster's gravity influences the Great Attractor itself, creating a domino effect of motion across hundreds of millions of light-years. Our local group, the Great Attractor, and countless other galaxies are all part of this vast flow, like leaves caught in a gentle but relentless river current. Modern telescopes piercing through the zone of avoidance with infrared and radio eyes have revealed glimpses of the Great Attractor's true nature. It's not a single massive object, but a dense knot in the cosmic web, a convergence point where filaments of dark matter and galaxy clusters intersect. The Norma cluster sits at its heart, surrounded by hundreds of other galaxies, all contributing to the gravitational pull we feel. yet even combined, their visible mass can't fully account for the strength of the attraction, hinting at unseen reservoirs of dark matter woven through the structure. The implications are staggering. If the great attractor's pull continues unchecked, the Milky Way and its neighbors will eventually merge with this enormous concentration of mass billions of years from now, becoming just another thread in its vast tapestry. But long before that happens, the expanding universe may render the journey endless, stretching space faster than we can traverse it. For now, we're caught in the current, swept along by forces that remind us how small our galactic home really is in the grand flow of the cosmos. Galaxies don't always play fair. Some cloak themselves behind thick curtains of cosmic dust, invisible to traditional telescopes. These hidden giants emit staggering amounts of energy, but their light gets trapped by swirling clouds of dust particles, leaving them nearly undetectable in optical wavelengths. That's where infrared astronomy comes in, peeling back these dusty veils to reveal some of the most violent and luminous objects in the universe. Take the era's galaxies, named after the infrared astronomical satellite that first spotted them in the 1980s. These cosmic enigmas glow hundreds of times brighter than our Milky Way, yet until infrared eyes turned toward them, they were practically ghost stories. The secret lies in their dust-shrouded cores, where frenzied starburst or ravenous supermassive black holes generate unimaginable heat. The dust absorbs this energy, re-emitting it as infrared radiation, invisible to human eyes but unmistakable to instruments like the James Webb Space Telescope. What makes these galaxies so extreme? Many are caught in the throes of titanic collisions, their gas and dust stirred into chaos by gravitational forces. As galaxies merge, vast reservoirs of interstellar material get funneled toward their centers, compressing until they ignite waves of star formation so intense they outshine entire normal galaxies. Others host active galactic nuclei, supermassive black holes feasting on captured material, their accretion disks glowing white-hot beneath the dust. Either way, the energy produced is so immense it heats the surrounding dust to scorching temperatures, turning these galaxies into infrared beacons across cosmic distances. The most luminous of these hidden monsters are the ultraluminous infrared galaxies, or ULIRG, which radiate more than 99% of their energy in the infrared. Some, like Oort 220, are the result of two massive spiral galaxies slamming together, their collision triggering firestorms of star formation while shrouding the chaos in dust. Others, like FSC 1530+242, defy expectations entirely. Their infrared brightness suggests activity far beyond what their visible structure should allow, hinting at processes we're only beginning to understand. Without infrared telescopes, we'd miss this hidden chapter of galactic evolution entirely. Optical surveys see only the tip of the iceberg, while infrared observations reveal the furious activity beneath. It's like listening to a symphony through a wall. You might catch the bass notes, but only by stepping inside do you hear the full orchestra, and the implications stretch beyond mere detection. Dust-obscured galaxies may hold clues to how the universe's most massive galaxies grew so quickly in its youth. Some theorists suggest they're a phase all giant galaxies go through, a messy, dust-choked adolescence before emerging as brilliant quasars or serene ellipticals. Others suspect they're the precursors to modern galaxy clusters, their violent mergers seeding the dense environments we see today. One thing's certain, the universe is far richer and far dustier than we ever imagined. Every time we build a telescope capable of seeing deeper into the infrared, we uncover new layers of this hidden cosmos, proving that sometimes the most extraordinary things are lurking right in front of us, just out of sight. For nearly 400,000 years after the Big Bang, the universe was a thick, soupy darkness, not because there was no light, but because space was packed so tightly with hydrogen atoms that light couldn't travel freely. This cosmic fog bank, known as the Dark Ages, persisted until something extraordinary happened. the first galaxies switched on their stellar floodlights, burning away the haze in an event astronomers call the Epoch of reionization. These infant galaxies were unlike anything we see today, small, fragile, and blazing with the universe's first generations of stars. Born from collapsing clouds of hydrogen and dark matter, their stars were monsters, hundreds of times more massive than our Sun and millions of times brighter. Their ultraviolet radiation acted like cosmic blowtorches, stripping electrons from surrounding hydrogen atoms in a process called ionization. Slowly but surely, these bubbles of ionized gas expanded, eating away at the primordial fog until eventually the entire universe became transparent. The scale of this transformation is hard to overstate. Imagine a frozen lake at dawn, its surface covered in thick ice. As sunlight touches the ice, it melts in patches, those pools growing until the entire lake is liquid again. That's what happened to the universe, except instead of sunlight, it was starlight, and instead of a lake, it was the entirety of space. The process wasn't instant. It took hundreds of millions of years, progressing unevenly as galaxies flickered to life in distant pockets of the cosmos. Some regions ionized early, others held onto their hydrogen fog longer, creating a cosmic patchwork of light and shadow. What's fascinating is how delicate this balance was. Too few stars, and the universe might have remained opaque indefinitely. Too many, and the radiation could have blown apart the very gas needed to form future galaxies. Instead, the timing was perfect, just enough ionization to clear the fog, but not so much that it disrupted the next chapter of cosmic evolution. We can still see echoes of this epoch today. The most distant quasars, lighthouses powered by supermassive black holes, reveal absorption lines in their light, showing where wisps of lingering neutral hydrogen once blocked their glow. Meanwhile, the cosmic microwave background carries faint imprints of the moment when the fog lifted, a snapshot of the universe's grand coming-of-age party. And here's the kicker: without this reionization, we wouldn't be here. A permanently opaque universe would have trapped light forever, preventing galaxies from ever growing as large and complex as they are today. The fact that we can peer billions of light years into space, tracing the web of galaxies back to their origins, is a direct result of those first plucky starlights punching holes in the darkness. It's a reminder that even in the vastness of the cosmos, small beginnings can lead to universe-altering change. The first stars in the universe were cosmic purists, pristine spheres of hydrogen and helium untouched by the heavier elements we now take for granted. But when these massive pioneers reached the end of their brief, fiery lives, they didn't fade quietly. Their explosive deaths as supernova became the universe's first alchemists, forging carbon, oxygen, iron, and other metals, as astronomers call any element heavier than helium in their final moments. These newly minted elements didn't stay put. They were blasted into space at nearly the speed of light, seeding surrounding gas clouds with the raw materials for everything from rocky planets to human DNA. This recycling process fundamentally changed the cosmos. Each subsequent generation of stars formed from gas increasingly enriched with these metals, like chefs adding new ingredients to a cosmic recipe. The oldest known stars, such as those in the Milky Way's halo, contain less than 1/1,000,000th the metal content of our Sun, a testament to their ancient origins. Meanwhile, younger stars like those in Orion's bustling stellar nurseries are practically swimming in heavy elements, their chemistry reflecting billions of years of stellar contributions. The mechanics behind this enrichment are as violent as they are beautiful. When a massive star goes supernova, temperatures in its core spike to over 100 billion degrees, hot enough to fuse atoms into heavier elements through a rapid-fire sequence of nuclear reactions. The explosion then scatters these freshly minted metals across light years of space. Some get incorporated into vast molecular clouds, where gravity eventually pulls them into new stars and planets. Others hitch rides on stellar winds or get swept up in galactic fountains, eventually raining back down to reignite star formation elsewhere. Some supernovae are even more prolific than others. Type Ia supernova, the thermonuclear detonations of white dwarf stars, are particularly efficient at dispersing iron and nickel. These elements become the backbone of terrestrial planets, including Earth's metallic core. Without such events, our world might never have formed. Meanwhile, neutron star mergers, the spectacular collisions of stellar corpses, create gold, platinum, and uranium in staggering quantities. A single neutron star merger can produce more heavy elements in seconds than all the supernova in a galaxy over centuries. The evidence for this enrichment is everywhere. Spectrographs reveal metal-rich stars clustered in the Milky Way spiral arms, where active star formation continues today. Meanwhile, ancient metal-poor stars huddle in the galactic halo, relics of a simpler time before supernova had seasoned the cosmic soup. Even intergalactic space isn't empty. It's laced with trace metals from countless explosions over billions of years, a faint metallic aftertaste lingering from the universe's most violent events. What's astonishing is how quickly this transformation occurred. Within just 1 billion years of the first stars igniting, some galaxies already had enough metals to form rocky worlds. By the time our Sun was born 4.6 billion years ago, the interstellar medium in our corner of the Milky Way was already rich with enough heavy elements to forge thousands of Earths. This rapid enrichment suggests early galaxies were far more efficient at recycling materials than we once thought, supernova acting as cosmic composters, turning stellar ashes into the building blocks of new solar systems. Yet the story isn't uniform. Some dwarf galaxies, isolated from the bustling galactic mainstream, remain stuck in a time warp, their stars stubbornly metal-poor despite the universe's age. Others, like those in dense galaxy clusters, show signs of hyper-enrichment from generations of supernova crammed into small volumes. These outliers prove that while metal enrichment is universal, its pace and extent depend entirely on a galaxy's environment and history. Looking ahead, the process shows no signs of stopping. Every supernova today continues this grand elemental legacy, adding new metals to the galactic reservoir. Future stars will inherit an even richer periodic table, potentially enabling worlds and chemistry we can scarcely imagine. It's a reminder that we, and everything around us, are literally made from the remnants of stars that died billions of years ago, their final acts still echoing in the atoms of our bodies and the rocks beneath our feet. Picture the Milky Way as a perfectly flat vinyl record, spinning gracefully in the cosmic jukebox of the universe. Now imagine someone took that record and gently bent its edges upward on one side, downward on the other. That's the reality of our galaxy's shape. Far from the pristine disk we often envision, the Milky Way is twisted into a subtle but unmistakable warp, with its outer regions curving like the brim of a cosmic fedora. This galactic distortion stretches nearly 5,000 light-years from the plane of the disk, a gentle cosmic wave frozen in space and time. What could bend an entire galaxy? The leading suspects read like a cosmic detective's case file. One prime candidate is the Milky Way's tumultuous history of galactic collisions. The Sagittarius dwarf galaxy, currently being torn apart by our galaxy's gravity, isn't the first interloper to cross our path. Over the past 11 billion years, this pesky satellite has punched through the Milky Way's disk at least 3 times, each pass sending gravitational shockwaves rippling through our galaxy's gas and stars. Like a stone skipping across a pond, these encounters could have torqued the outer disk into its current warped state. But there's another, more mysterious possibility: dark matter's invisible hand. Recent simulations suggest the Milky Way's dark matter halo. The vast, unseen cocoon of matter surrounding our visible galaxy might be lopsided. If this halo is denser or shaped differently on one side, its gravitational pull could be yanking the outer disk out of alignment. Think of it like a lopsided tire on a car. The uneven weight distribution makes the whole structure wobble over time. The warp isn't just a curiosity, it's a dynamic feature teeming with activity. Observations reveal this bent region contains younger, bluer stars than the galactic average, suggesting gas is still actively forming new stars in these twisted outskirts. Meanwhile, the warp's rotation lags behind the inner disk by about 20%, creating a celestial tug of war between gravity's pull and the galaxy's overall spin. Here's where it gets truly bizarre. The warp isn't static but undulates around the galaxy like a slow-motion wave, completing one full oscillation every 600 to 700 million years. Our solar system, currently positioned near the galactic plane, will find itself above the warp in about 100 million years, though the change is so gradual we'd never notice. This bending of our cosmic home challenges textbook illustrations of galaxies as flat, orderly structures. Instead, warps appear to be the rule rather than the exception. Over half of all spiral galaxies show similar distortions. Some, like the nearby ISO 510-051, exhibit warps so extreme they resemble taffy stretched by an invisible hand. Yet the Milky Way's warp holds unique clues about our place in the cosmos. Its orientation aligns suspiciously well with the orbital plane of the large Magellanic Cloud, hinting that this satellite galaxy's gravitational pull might be twisting us out of shape. Other researchers point to the galactic bar, the dense, elongated structure at our galaxy's core, as a possible driver of the warp through complex resonances that ripple outward. New data from space telescopes like Gaia are transforming our understanding of this celestial contortion. By precisely mapping the positions and motions of billions of stars, astronomers have discovered the warp isn't just bending, it's precessing, gradually changing its orientation over time. This slow wobble might hold the key to measuring the invisible dark matter halo's true shape, offering insights into the mysterious substance that outweighs all visible matter in our galaxy. So the next time you gaze at the Milky Way's glowing band arcing across the night sky, remember, you're not looking at a flat highway of stars but a cosmic roller coaster, its edges twisted by forces both seen and unseen, a testament to the dynamic, ever-changing nature of even the most familiar galactic landscapes. Dragonfly 44 isn't supposed to exist. This cosmic paradox floating in the Coma galaxy cluster is as wide as the Milky Way, yet its stars are spread so thin they barely register against the darkness. If our galaxy were a bustling metropolis, Dragonfly 44 would be a ghost town, its few streetlights spaced miles apart, flickering in an ocean of night. But here's the real shocker. Despite its size, this galaxy weighs almost nothing. The stars account for less than 1% of its mass, the rest an unfathomable halo of dark matter, silent and invisible, holding this wispy giant together against all odds. Ultra-diffused galaxies like Dragonfly 44 shatter every expectation we have about how galaxies form. They defy the basic rule that visible matter, stars and gas should dominate a galaxy's structure. Instead, these cosmic enigmas are more like dark matter clouds that accidentally trapped a handful of stars. Their existence forces us to ask, did dark matter clump differently in certain parts of the universe? Or did some violent event strip away their gas and stars, leaving behind only the barest skeleton of what was once a thriving galaxy? The mystery deepens when you realize how many of these ghosts are hiding in plain sight. Traditional surveys missed them for decades because their stars are so sparse they blend into the background. Only with advanced telescopes equipped with ultra-sensitive detectors like the Dragonfly telephoto array that discovered Dragonfly 44 did these spectral giants snap into focus. Now we know they're everywhere, particularly in dense galaxy clusters where gravitational tides might have stretched them into their current, ethereal forms. But the real head-scratcher is how they survive at all. In most galaxies, the gravitational pull of dark matter and visible matter work in tandem. Remove too much visible mass and the galaxy should fly apart. Yet ultra-diffuse galaxies like Dragonfly 44 cling to existence with barely any stars to anchor them. Their dark matter halos must be oddly concentrated, like invisible glue binding stars that would otherwise drift into the void. Some theories suggest these galaxies are failed giants, their dark matter halos primed to host a Milky Way's worth of stars, but star formation fizzled before it could fill the space. Others propose they're the battered remnants of once normal galaxies, their stars ripped away by repeated collisions, leaving only their dark matter intact. The implications ripple far beyond these cosmic oddities. If dark matter can sculpt galaxies this large yet this faint, our entire understanding of galactic evolution might need rewriting. Could there be even darker galaxies out there, halos of pure dark matter with no stars at all? And what does this mean for the so-called missing satellite problem, where simulations predict thousands of dwarf galaxies around the Milky Way, but we've only found a fraction? Ultra-diffuse galaxies might be the missing link hiding in plain sight, their true nature masked by their ghostly light. Dragonfly 44 and its cousins challenge us to rethink the boundaries of what a galaxy even is. They're not just faint versions of the galaxies we know. They're something entirely different, a shadow universe where dark matter calls the shots and stars are mere afterthoughts. As telescopes peer deeper into the cosmos, these whisper-thin giants remind us that the universe still holds galaxies we can't explain, lurking at the edge of visibility, waiting to upend everything we thought we knew. In December 1995, astronomers working with the Hubble Space Telescope took a risk. They pointed the observatory at what appeared to be an empty patch of sky near the Big Dipper, a spot no larger than a grain of sand held at arm's length. Over 10 consecutive days, Hubble collected every precious photon it could, compiling them into a single image. What emerged from that gamble wasn't darkness, but a staggering tapestry of light. Nearly 3,000 galaxies, each a swirling island of stars, packed into a sliver of space so small most telescopes would have dismissed it as void. The Hubble Deep Field didn't just capture distant objects, it shattered humanity's understanding of the universe's scale and our place within it. Before this image, astronomers knew the cosmos was vast, but the deep field made that abstraction visceral. Every speck and smudge represented entire galaxies, some as they looked just a few billion years after the Big Bang, crowded into a fraction of the sky. Suddenly, the observable universe wasn't merely large, it was teeming with galaxies beyond counting, each containing billions of stars. Projected across the entire celestial sphere, this density suggested the cosmos could hold over 100 billion galaxies in total, a number so vast it redefined immensity itself. The true revolution lay in the diversity of those galaxies. Unlike the orderly spirals and ellipticals seen in our cosmic neighborhood, the deep field revealed galaxies in every stage of evolution, misshapen fragments still assembling, colliding giants spewing stellar debris, and faint red smudges representing the earliest galactic building blocks. This wasn't a static universe, it was a living museum of galactic history, with younger, bluer galaxies dominating the distant reaches, their light fossilized from eras when star formation raged unchecked. Perhaps most profound was how the deep field humbled our perspective. That empty patch of sky, devoid of bright stars or known objects, turned out to be one of the most densely populated regions ever photographed. It forced us to confront a fundamental truth: the universe doesn't care what we consider empty or significant. Every direction we look, no matter how barren it seems, is a tunnel through space and time, lined with galaxies whose light has traveled eons to reach us. The legacy of that image echoes in every deep field observation since. Hubble's successors, like the Ultra-Deep Field and the Extreme Deep Field, pushed even further, revealing galaxies so distant their light dates back to just 400 million years after the Big Bang. Each iteration reaffirms the same lesson: the cosmos is vaster, stranger, and more abundant than we ever imagined, yet the deep field's impact transcends astronomy. It reshaped culture, philosophy, and our existential bearings. For the first time, humanity held visual proof that our galaxy is one insignificant speck in an ocean of stars, not the center of creation, but a single note in a galactic symphony stretching across billions of light years. It's a reminder that when we dare to stare into the seeming void with patience and curiosity, the universe often stares back with wonders we never anticipated. When galaxies collide head-on, the universe transforms violence into breathtaking geometry. Ring galaxies are the proof. Hoag's object, a celestial bullseye floating 600 million light-years away, defies every expectation of galactic chaos. At its core sits a dense, golden sphere of ancient stars, while around it stretches a near-perfect circle of younger, blue stars, separated by a dark, almost empty gap. This cosmic ripple wasn't crafted by delicate forces. It was forged in a collision so precise it turned destruction into art. The secret lies in the physics of a direct hit. When a smaller galaxy plunges straight through the heart of a larger disk galaxy, the impact sends shockwaves racing outward through the larger galaxy's gas like ripples in a pond. As these waves reach the outer disk, they compress the gas into a dense ring, triggering a firestorm of new star formation. The result, a radiant circle of young, hot stars blazing against the darkness, while the galaxy's original core, largely untouched by the collision, glows serenely at the center. It's a celestial bullseye with stellar birth and cosmic violence frozen in a single, fleeting snapshot. Hoag's object isn't alone in this rarity. The Cartwheel Galaxy, another stunning ring structure, shows the aftermath of a smaller galaxy punching through its center, its ripple-like ring stretching 150,000 light-years across. Infrared observations reveal the hidden mechanics. The collision's shockwave ignited a starburst so intense it temporarily outshone the Milky Way by a factor of 10. Yet despite their beauty, these rings are temporary. Over hundreds of millions of years, gravity will distort the perfect circles, scattering stars back into more chaotic orbits until the ring fades into the galaxy's background. What makes these collisions special isn't just their precision, it's their rarity. Most galactic encounters are glancing blows, creating the tangled spirals and tidal tails we commonly associate with mergers. For a ring to form, the incoming galaxy must strike almost dead center, like a bullet passing through the exact middle of a spinning dartboard. Even a slight deviation would twist the ring into a lopsided arc or disrupt it entirely. That's why fewer than 1 in 10,000 galaxies displays this perfect circular structure. The universe favors chaos over order, making Hoag's object and its kin cosmic jackpots of alignment and timing. Here's the twist: some ring galaxies might not need collisions at all. A handful, like NGC 7220, exhibit rings with no visible culprit, no second galaxy nearby to blame for the disruption. Astronomers suspect these could be the ghosts of long-ago mergers, where the intruder galaxy merged completely, leaving only the ripple of its passage behind. Others might form through internal instabilities, where the galaxy's own bar-like structure funnels gas outward in a self-sustaining wave. But Hoag's object remains the gold standard, its symmetry so flawless it's inspired debates about whether some unknown physics, or even a freak resonance with dark matter, could play a role. These galactic rings are more than just pretty anomalies. They're cosmic laboratories offering snapshots of how gas behaves under extreme conditions. The star-forming rings act like petri dishes for studying stellar birth rates, while the central bulges preserve clues about the galaxy's pre-collision history. Some even harbor supermassive black holes that woke from dormancy during the collision, their outbursts adding another layer of complexity to the system. Perhaps most mesmerizing is what these rings imply about perspective. From our vantage point, Hoag's object appears perfectly aligned, but tilt the galaxy slightly and the ring would warp into an ellipse. That means somewhere in the universe there could be thousands more ring galaxies hiding in plain sight, their symmetry disguised by angle alone. It's a reminder that even the most extraordinary cosmic phenomena depend on where and when we happen to be looking. The Milky Way and Andromeda aren't just neighbors, they're star-crossed lovers locked in a gravitational embrace that will inevitably pull them together in one of the universe's most spectacular slow-motion mergers. Right now, Andromeda barrels toward us at 250,000 miles per hour, but don't panic just yet. This cosmic collision won't truly begin for another 4 billion years. When it does, the night sky will transform in ways that defy imagination. At first, the changes will be subtle. As Andromeda looms closer, its faint smudge in the constellation bearing its name will swell into an unmistakable disk, eventually rivaling the full moon in apparent size. Gravity's invisible hand will begin sculpting both galaxies long before they touch, warping their spiral arms into elongated tidal tails that stretch across tens of thousands of light years. Stars won't collide, space is too vast, but the interstellar gas clouds within both galaxies will slam together with unimaginable force, igniting fireworks of star formation so intense they'll outshine all other cosmic events in our galaxy's history. The actual merger will take billions of years to complete. After their first close pass, the Milky Way and Andromeda will recoil like cosmic yo-yos, only to be pulled back together by their combined gravity. Each subsequent swing will strip away more stars and gas, scattering them into a growing halo of luminous debris. The galaxy's supermassive black holes, Sagittarius, a star in the Milky Way, and Andromeda's even larger counterpart, will begin their own deadly dance, circling each other in ever-tightening orbits until they finally merge in a burst of gravitational waves. By the time the dust settles roughly 6 billion years from now, the two spirals will have morphed into a single, football-shaped elliptical galaxy astronomers whimsically call Milky-Andromeda. This new titan will bear little resemblance to its parents. The elegant spiral arms that once defined both galaxies will be erased, their stars redistributed into a smooth, featureless glow. Thousands of globular clusters, ancient spherical collections of stars from both galaxies, will orbit the new core like bees around a hive. Yet even this colossal merger won't be the end. The local group's smaller galaxies, Triangulum, the Magellanic Clouds, and dozens of dwarf satellites will eventually be absorbed into Milky-Andromeda's growing bulk. Within 10 billion years, all major galaxies in our local neighborhood will consolidate into one dominant system, floating in an ever-expanding universe where other galaxy groups have faded beyond visibility. What's astonishing isn't just the scale of this transformation, it's how little it will disrupt individual solar systems. Earth, if it still exists, will likely survive unscathed, though our night sky will be unrecognizable. The familiar Milky Way band will vanish, replaced by a haze of blended starlight and the glowing remnants of the merger. New constellations will form from stars born in the collision, their patterns reshuffled by the galactic dance. This future might seem unfathomably distant, but it's written in the stars, or rather, in the unyielding laws of gravity that have guided the cosmos since its birth. The Milky Way and Andromeda's fate is a microcosm of the universe's grand narrative, a story where even the mightiest structures are transient, destined to merge and evolve on scales that humble human imagination. Long after our sun has faded, the legacy of these two galaxies will live on not as separate entities, but as a single, shining testament to the universe's endless capacity for reinvention. Imagine a cosmic game of billiards where a blazing quasar acts as the cue ball, striking invisible gas clouds around a galaxy and making them glow. These ghostly echoes of light, known as quasar illumination, let astronomers map the hidden structure of galaxies we'd otherwise never see. It's like shining a flashlight through fog. Suddenly, the invisible becomes vivid, revealing tendrils of gas stretching far beyond a galaxy's visible stars. The process starts with quasars, supermassive black holes at the hearts of distant galaxies, devouring matter so ferociously they outshine entire galaxies. Their intense ultraviolet radiation acts like a cosmic spotlight, penetrating gas clouds millions of light-years away. When this light hits hydrogen atoms, it energizes them, causing the gas to fluoresce in a specific shade of ultraviolet called Lyman alpha emission. The result, a galactic silhouette painted in light, with filaments and halos glowing against the darkness. One of the most stunning examples is the Lyman alpha blob Lab 1, a massive cloud of hydrogen illuminated by a hidden quasar. Stretching 300,000 light-years, 3 times the Milky Way's diameter, this glowing nebula revealed a vast spiderweb-like structure of gas-fueling galaxy growth. Without the quasar's backlighting, LAB-1 would have remained invisible, its delicate filaments lost in the void. But the real magic lies in what these echoes teach us. By analyzing the light spectrum, astronomers can read the gas's composition, temperature, and motion like a cosmic fingerprint. Some clouds race toward us, others flee, painting a dynamic picture of galactic winds and inflows. In 2018, observations of a quasar-lit galaxy showed gas streaming inward at 1,000,000 miles per hour, direct evidence of galaxies breathing in fresh material to form stars. The echoes also expose galactic violence. Around the quasar UM-287, scientists found a gas streamer 650,000 light-years long, the aftermath of a dwarf galaxy torn apart by tidal forces. Like ink dropped in water, the debris trail revealed the gravitational turmoil happening just out of sight. Yet this technique has limits. Quasars are rare and their beams are narrow, meaning we only see slices of illuminated gas. It's like exploring a cave. With a single flashlight you glimpse stunning formations, but the full cavern remains unseen. New tools like the James Webb Space Telescope are overcoming this by detecting fainter echoes, mapping gas structures in unprecedented detail. What's breathtaking is how fleeting these echoes are. Quasar light illuminates gas for mere thousands of years, a blink in cosmic time. We're catching these galaxies in a single luminous moment, like photographing a firefly's glow in a vast, dark forest. Each echo is a time capsule, preserving a snapshot of galactic anatomy that would otherwise fade into the endless night. The Milky Way doesn't drift through a typical corner of the cosmos. We're floating inside a cosmic no-man's land, a staggering void so vast it defies expectations. Known as the KBC Void, named after astronomers Keenan, Barger, and Cowie who identified it, this spherical emptiness stretches over 2 billion light-years across, making it the largest known structure of its kind. If you pictured the universe's matter spread evenly like sprinkles on a donut, the KBC Void is the inexplicable blank bite where almost nothing sticks. What makes this emptiness so strange? Standard cosmological models suggest matter should clump somewhat uniformly, with galaxies nested in a web-like structure of filaments and nodes. Instead, our galactic neighborhood feels like a deserted island in an ocean of darkness. The Milky Way-Andromeda and a handful of other galaxies huddle together in this void's sparse outskirts, while beyond its borders, galaxy clusters pack together like bustling cities. It's as if we're perched on the edge of a cosmic canyon, peering across an abyss at the glowing metropolises of the universe. How did this void form? One theory points to a colossal interplay of forces in the early universe. During inflation, the rapid expansion just moments after the Big Bang, quantum fluctuations might have created regions slightly emptier than others. Over billions of years, gravity amplified these differences, pulling matter toward denser areas and leaving behind vast, underdense bubbles. Another possibility is that multiple smaller voids merged over time, their combined emptiness sculpting the KBC's jaw-dropping scale. Living inside a void isn't just a curiosity, it warps our cosmic perspective. Because we're surrounded by so little matter, measurements of the universe's expansion rate, the Hubble constant, could be skewed. When astronomers observe distant supernova or galaxies, they're peering out of the void into denser regions, potentially misjudging distances and speeds. This might explain some discrepancies between different methods of calculating the universe's expansion, a debate currently dividing cosmology. The KBC void also raises existential questions. Is our placement here just a fluke, or does it hint at deeper principles? Some theorists suggest voids play a crucial role in galaxy evolution. Their low-density environments might allow galaxies like ours to grow undisturbed, free from the gravitational chaos of crowded clusters. Others speculate that voids could be incubators for mysterious dark energy, their emptiness allowing this enigmatic force to dominate and accelerate the universe's expansion. Yet the most humbling thought is this: if intelligent life exists elsewhere, civilizations inside dense galaxy clusters might gaze into their star-packed skies and assume the universe is far more crowded than it truly is. Meanwhile, we float in our quiet pocket of space, our view of the cosmos framed by an absence so vast it reshapes how we understand reality itself. The KBC void isn't just empty space, it's a reminder that even the grandest structures in the universe are filled with paradoxes, and our place within them is far stranger than we ever imagined. Quasars aren't just the brightest objects in the universe, they might also be the seeds from which galaxies grow. These dazzling beacons, powered by supermassive black holes feasting on cosmic gas, don't just sit at the centers of galaxies, they could have played a crucial role in creating them. In the chaotic early universe, quasars may have acted like gravitational anchors, pulling in vast clouds of gas and dark matter that eventually coalesced into the first galactic structures. Imagine a tiny pearl forming around a grain of sand, except in this case, the grain is a voracious black hole, and the pearl becomes an entire galaxy. The evidence lies in the sheer number of quasars spotted in the distant universe, their light reaching us from eras when galaxies were just beginning to assemble. Many of these quasars appear embedded in massive halos of gas, their radiation ionizing surrounding material while their gravity molds it into dense star-forming regions. It's a paradoxical process. Quasars blast out enough energy to sterilize entire galaxies, yet their gravitational pull also gathers the raw materials needed to build them. Some of the earliest known galaxies, like those observed just 600 million years after the Big Bang, already contain supermassive black holes weighing billions of suns. That's an impossible growth spurt unless these black holes were there first, acting as kernels around which galaxies crystallized. One compelling theory suggests that quasars didn't just influence galaxy formation, they jump-started it. When the first supermassive black holes ignited, their intense radiation and powerful jets could have compressed nearby gas clouds, triggering waves of star formation even as they devoured matter. Like cosmic blacksmiths, they forged the very structures they would later call home. This might explain why the most massive galaxies in the universe often host the most massive black holes. Not because the galaxy fed the black hole, but because the black hole helped build the galaxy from the ground up. But here's the catch: not all quasars lead to galactic success stories. Some may have blown away their surrounding gas too violently, leaving behind stunted galaxies or dark matter halos with no stars at all. Others, like the quasar J03131806 observed in the infant universe, appear to be growing faster than their host galaxies, suggesting their relationship is more complex than a simple partnership. It's a delicate balancing act: too much quasar activity and the galaxy starves; too little and it might never fully form. The legacy of these quasar-seeded galaxies lingers today. The Milky Way's central black hole, Sagittarius A star, is a quiet shadow of its brilliant ancestors, but its presence hints at a tumultuous past. Even now, it subtly shapes the orbits of stars near the galactic center, a remnant of the forces that may have sculpted our entire galaxy. Across the cosmos, the echoes of quasars live on in the supermassive black holes at the hearts of galaxies, silent witnesses to an era when light carved darkness into the structures we now call home. Rising from the Milky Way's core like twin titans, the Fermi bubbles stretch 50,000 light-years into space, one erupting above our galactic plane, the other plunging below. These colossal structures, discovered in 2010 by NASA's Fermi Gamma-ray Space Telescope, glow with high-energy gamma rays, their faint outlines tracing an hourglass-shaped monument to some cataclysmic event buried in our galaxy's past. What makes these bubbles astonishing isn't just their scale enough to engulf half our visible sky if we could see them, but their origin story, which points to a violent tantrum from our supermassive black hole, Sagittarius, a star that shook the galaxy millions of years ago. The bubble's gamma-ray emissions suggest they're filled with ultra-fast particles moving near light speed, likely accelerated by some tremendous energy release from the galactic center. Imagine detonating a cosmic bomb so powerful its shockwaves carve cavities in the thin gas between galaxies. That's the scale of violence required to create structures this immense. Recent measurements reveal the bubble's edges are remarkably sharp, like the boundaries of a soap bubble, indicating the eruption happened quickly by cosmic standards, possibly within 100,000 years. This wasn't a slow leak of energy, but a sudden, catastrophic belch from the black hole that sent jets of plasma screaming outward at millions of miles per hour. But here's where it gets strange. These bubbles are asymmetric. The northern bubble extends slightly farther than its southern counterpart, a lopsidedness that hints at an uneven explosion or perhaps resistance from unseen gas clouds on one side. Some astronomers propose the blast wasn't a single event, but a series of outbursts over millennia, each adding to the structure like layers of volcanic ash. Others suspect the bubbles might be older than we think, relics from an even more active period in our black hole's youth, their gamma rays only recently detectable as technology improved. The leading theory traces the bubbles to a feeding frenzy roughly 2 to 4 million years ago, when Sagittarius, a star, devoured an enormous cloud of gas, or perhaps a wayward star. As material spiraled inward, some got channeled into powerful jets along the black hole's spin axis, punching through the galaxy's gas and creating these vast cavities. The timing aligns with curious evidence from other wavelengths. A glow of ultraviolet light detected in the Magellanic stream, a river of gas orbiting the Milky Way, suggests our galaxy's core briefly outshone all its stars combined during this period. Even more telling, the bubbles coincide with mysterious X-ray structures called the E-Rosetta bubbles, discovered in 2020, which show hot gas at slightly lower energies, like an echo of the same event seen through different eyes. What's unfolding now is a cosmic detective story. The Fermi bubbles aren't static fossils, they're dynamic structures still influencing our galaxy. Their outer edges interact with the Milky Way's halo gas, creating shock waves that might trigger star formation in distant clouds. Meanwhile, particles trapped inside the bubbles rain back down onto the galactic disk, potentially seeding new chemistry in interstellar space. Some researchers even speculate these particle showers could affect Earth's atmosphere over geological timescales, though the evidence remains speculative. This discovery has rewritten our understanding of galactic cores. Once thought to be relatively quiet neighborhoods, we now know they can unleash energies rivaling supernova not just once, but repeatedly over cosmic time. The Fermi bubbles stand as a reminder that even our seemingly placid Milky Way has a violent history, its calm spiral arms hiding eruptions powerful enough to reshape the galaxy itself. And with our black hole currently in a quiet phase, they offer a sobering glimpse of what might happen when it next awakens. Some galaxies don't just make stars, they manufacture them on an industrial scale, cramming millions of suns into clusters so dense they'd fit inside the distance from Earth to Alpha Centauri. The Tarantula Nebula, a swirling nest of gas and young stars in the large Magellanic Cloud, hosts some of the most extreme examples, superstar clusters glowing with the intensity of 1,000,000 suns packed into regions barely 50 light-years across. If our sun were born in such a neighborhood, the night sky would blaze with thousands of stars as bright as Venus, all close enough to outshine the full moon. What makes these clusters so extraordinary is how they defy normal stellar etiquette. In our Milky Way, star-forming regions like Orion produce a few thousand stars spaced light-years apart. But superstar clusters operate under different rules. Their clouds of gas collapse under such intense pressure that stars form shoulder to shoulder, reaching densities 10,000 times higher than our local stellar environment. The result is cosmic pandemonium, massive stars, each dozens of times heavier than our sun, burning ferociously and dying young in supernova explosions that rattle the cluster's very foundations. The champion of these stellar metropolises is R136, the heart of the Tarantula Nebula. Within a volume smaller than the Orion Nebula, this cluster contains over 100,000 stars, including some of the most massive ever recorded. Stars like R136A1, a behemoth weighing 260 solar masses, shine with nearly 9 million times our sun's luminosity, their ultraviolet radiation sculpting the surrounding nebula into fantastical pillars and bubbles. Such extreme conditions only last a few million years before the heaviest stars explode, but in that brief window they rewrite the rules of stellar physics. Why do some galaxies spawn these superclusters while others don't? The answer lies in the perfect storm of conditions: vast reservoirs of dense gas, turbulent motions that prevent premature star formation, and often the gravitational kick of a nearby galaxy interaction. The Large Magellanic Cloud, for instance, owes its spectacular star-forming regions to repeated close encounters with the Milky Way, which compressed its gas into the ideal breeding grounds for superclusters. Other galaxies, like the famous antennae colliding pair, show similar clusters forming in the wreckage of their collision, proving that galactic violence often sparks stellar fireworks. But these clusters face a turbulent future. Their densely packed stars constantly interact gravitationally, flinging some members into interstellar space while others merge into even more massive stars. Over hundreds of millions of years, the clusters will expand, their outer stars stripped away by galactic tides until only a tight core remains, the blueprint for the globular clusters we see orbiting older galaxies today. The legacy of superstar clusters extends far beyond their immediate spectacle. They may be the birthplaces of intermediate mass black holes, objects weighing hundreds or thousands of suns, formed through runaway stellar collisions. Some astronomers speculate these could be the missing link between star-sized black holes and the supermassive monsters lurking in galactic centers. Every supercluster is thus both a time capsule and a laboratory, offering glimpses into how the universe builds its most extreme structures under conditions we can scarcely replicate elsewhere. Far beyond the orbits of Neptune and Pluto, where sunlight is a faint memory, lies a frozen archive of our solar system's earliest days, the Oort cloud. This vast spherical shell of icy bodies stretches nearly a light-year into space, holding trillions of comets in cold storage. But these ancient ice balls aren't just relics of our sun's birth. They're cosmic time capsules carrying fingerprints of the Milky Way itself, forged from the same primordial gas and dust that built our galaxy over 4.6 billion years ago. The connection lies in their chemistry. Spectroscopic studies of long-period comets, those that originate in the Oort cloud, reveal molecular ingredients strikingly similar to the dense interstellar clouds where stars form today. Carbon monoxide, cyanide compounds, and even complex organic molecules detected in these comets match those found in the galaxy's coldest molecular clouds. This isn't a coincidence, it's evidence that the raw materials of the Oort cloud predate our solar system, inherited directly from the Milky Way's sprawling nurseries of gas and dust. Some of these ices might have condensed in the frigid outskirts of our galaxy's giant molecular clouds long before the sun ignited, preserved unchanged in the deep freeze of interstellar space. Gravity knitted these galactic leftovers into the solar system's outer reaches. As the young sun formed from a collapsing cloud of gas and dust, its gravitational influence carved out a rotating disk, the protoplanetary disk where planets would later assemble. But the outermost fringes of this disk remained a chaotic frontier where the sun's weak gravity competed with the tidal forces of passing stars and the Milky Way's overall gravitational field. Here, icy planetesimals, some as large as mountains, got scattered like billiard balls, flung into distant orbits where they accumulated into the Oort cloud. Crucially, this region also captured wandering interstellar ice chunks that hadn't belonged to the original solar nebula, making the Oort cloud a museum of both local and galactic history. The galaxy's architecture shaped this process. Our sun didn't form in isolation. It was born within a star cluster, surrounded by sibling stars that have since drifted apart. Close encounters with these neighbors in the solar system's first 100 million years would have perturbed icy bodies, pushing them outward while the Milky Way's tides organized them into a spherical shell. Even today, the Oort cloud isn't static passing stars, molecular clouds, and the gravitational pull of the galaxy's spiral arms occasionally dislodge comets, sending them hurtling inward where they light up our skies as spectacular visitors from the darkness. What's astonishing is how much of the Oort cloud remains untouchable. Unlike the Kuiper belt, a donut-shaped region of icy bodies closer to the sun, the Oort cloud's outermost reaches are so distant that they hover on the edge of the sun's gravitational grasp. At these extremes, the Milky Way's tides and random passing stars can strip comets away entirely, flinging them into interstellar space to become rogue wanderers. This means the Oort cloud we see today is just a fraction of its original population. Countless icy bodies have already been lost to the galaxy, carrying traces of our solar system's birth into the wider cosmos. Occasionally, the galaxy gives back. Astronomers tracking hyperbolic comets, those moving too fast to be bound by the sun's gravity, have identified interstellar interlopers like Oumuamua and Borisov. These visitors likely originated in other star systems, their own versions of Oort clouds ejected by galactic dynamics. Their chemistry mirrors our own comets, suggesting that the processes building icy reservoirs around stars are universal, part of the galaxy's grand cycle of material redistribution. The Oort cloud thus represents more than just a collection of frozen leftovers. It's a bridge between stellar and galactic scales. Every long-period comet that graces our inner solar system is a messenger from two distinct pasts, the chaos of our solar system's birth and the even older story of how the Milky Way transformed diffuse gas into the rich tapestry of stars and planets we see today. In their icy hearts, these comets carry not just water and organic molecules, but the very essence of our galactic origins. Galaxies aren't gentle diners. When they devour their neighbors, they leave behind stellar crumbs scattered across the cosmos. These cosmic breadcrumbs, known as tidal streams, are the ghostly remnants of smaller galaxies torn apart by gravitational forces, their stars stretched into dazzling ribbons that orbit their captors for billions of years. The Milky Way's halo is littered with these relics, but none tell a more dramatic story than the Gaia Enceladus stream, a vast river of stars wrapping around our galaxy like a celestial serpent, the fossilized evidence of a merger so violent it reshaped our galactic home forever. This ancient collision wasn't some delicate ballet. It was a brutal, slow-motion dismantling. Roughly 10 billion years ago, a dwarf galaxy now called Gaia Enceladus, named for the ESA's Gaia spacecraft that uncovered its remains, plunged into the young Milky Way. Gravity's tidal forces pulled the smaller galaxy apart like taffy, scattering its stars into chaotic orbits while the Milky Way's disk buckled and thickened under the impact. Today, these orphan stars move in stark contrast to the Milky Way's orderly rotation, tracing wild, looping paths that betray their foreign origins. Chemical analysis reveals their secret. These stars are metal-poor, forged in a galaxy born before supernova had seeded the universe with heavy elements, a living time capsule of the cosmos's raw early days. But Gaia Enceladus isn't alone. The Milky Way's halo shimmers with stellar streams, each a testament to galactic cannibalism. The Sagittarius stream, for instance, paints a glittering arc across the southern sky, the dying breath of a dwarf galaxy caught in a billion-year death spiral around our own. Then there's the Fermy stream, a group of stars with unusual orbits hinting at another ancient merger. Like forensic scientists reconstructing a crime scene, astronomers piece together these streams' motions and chemistry to reveal not just what was devoured, but how the angles of collision, the masses involved, even the timelines of these cosmic feasts. What's astonishing is how long these streams endure. Unlike gas clouds that dissipate or disperse, stellar streams once formed can persist for cosmic epochs, their stars drifting like confetti caught in a slow-motion whirlwind. Their survival depends on a delicate balance. Too close to the galactic center, and tidal forces shred them completely. Too far, and they lack the density to hold together. The fact that we see so many today suggests the Milky Way's appetite has been insatiable. Its halo a graveyard of galactic conquest stretching back to the universe's youth. These streams aren't just fossils, they're active participants in the Milky Way's evolution. As they loop around the galaxy, their gravity subtly perturbs the orbits of other stars and even dark matter, reshaping our galactic neighborhood in ways we're only beginning to understand. Some streams, like Phoenix, are still coalescing from recent disruptions, their stars not yet fully mixed into the halo's background. Others, like Cetus, are so diffused they're barely detectable, their existence revealed only by advanced algorithms sifting through millions of stellar motions. The real revelation: this carnage is universal. Andromeda's halo shimmers with its own streams, including the giant southern stream, a remnant of a devoured dwarf galaxy. Even distant galaxies show these telltale signatures: thin, luminous trails arcing through deep field images, evidence that cannibalism isn't just a local phenomenon but a fundamental driver of galactic growth. So the next time you gaze at the night sky, remember, those seemingly random stars might be part of an ancient river flowing silently through the darkness, a river born from violence, sculpted by gravity, and carrying within it the story of how galaxies feast, grow, and slowly rewrite their own histories. The James Webb Space Telescope isn't just observing the cosmos, it's tearing up the astronomy rulebook. Peering back further than any instrument before it, JWST has spotted galaxies thriving when the universe was just 300 million years old, a discovery that's forcing scientists to rethink how cosmic structures emerged from the primordial darkness. These aren't the faint, fledgling proto-galaxies theorists predicted. Their massive, mature systems glowing with starlight, their existence challenging our fundamental timelines of galactic evolution. One of JWST's most startling finds is Sears 93316, a galaxy shining just 235 million years after the Big Bang. What's baffling isn't just its age, it's its size. Packing billions of stars into a volume far smaller than the Milky Way, this cosmic toddler defies expectations that early galaxies should be small and fragile. Its stars already show signs of heavy elements, meaning generations had lived, died, and enriched their surroundings before we're even supposed to believe galaxies could form. It's like finding a thriving metropolis in what should be barren wilderness. The telescope's infrared eyes reveal why previous models fell short. Earlier observatories like Hubble saw the early universe as a patchwork of dim red dots, but JWST sensitivity uncovers intricate structures, spiral arms, clumps of star formation, even dust where none were thought to exist so soon. Glass Z13, another record breaker, shows a disk-like rotation when the cosmos was barely 4% of its current age, suggesting gravity worked faster than anyone imagined to sculpt order from chaos. These discoveries point to a radical possibility. The first galaxies didn't grow slowly from tiny seeds, but may have formed nearly full-fledged in giant leaps. Some theorists now propose that the early universe's denser gas collapsed directly into substantial galaxies under the weight of dark matter, bypassing the gradual merger process we see later. Others speculate that supermassive black holes detected in some of these ancient galaxies acted as gravitational anchors, accelerating star formation rates to breakneck speeds. Yet the biggest shock comes from the galaxy's brightness. Many outshine predictions by orders of magnitude, glowing with ultraviolet radiation so intense it should have torn apart their fragile gas clouds. This overluminosity problem hints at unknown physics, perhaps stars forming differently in the early universe, free from the heavy elements that later hindered their growth. Or maybe dark matter, the invisible scaffold of galaxies, clumped more efficiently in the hotter, denser conditions of the young cosmos. What's certain is JWST has exposed gaps in our cosmic origin story. Every deep field image peels back another layer of the universe's childhood, revealing a period far more dynamic and complex than simulations suggested. Far from being simple building blocks, these primordial galaxies were already shaping their surroundings, their light ionizing the surrounding hydrogen fog and carving the transparent universe we inhabit today. The telescope's revelations are just beginning, but one truth is already clear. The dawn of galaxies was brighter, bolder, and more beautiful than we ever dared to dream. Einstein's theory of relativity gave us an astonishing prediction. Mass doesn't just warp space, it bends light itself. And nowhere is this phenomenon more dramatic than when entire galaxies act as cosmic magnifying glasses, distorting and amplifying the light of objects hidden far behind them. This surreal effect, called gravitational lensing, transforms some of the universe's most massive galaxies into natural telescopes, revealing corners of the cosmos we'd otherwise never see. Picture a bowling ball placed on a trampoline. The weight creates a depression that sends marbles rolling toward it. Now imagine that depression is space-time, and the marbles are photons of light traveling from a distant quasar. As the light passes near a massive galaxy or cluster, space-time's curvature bends its path, just like water bending the image of a spoon in a glass. The result can be anything from a subtle smearing of background galaxies to perfect Einstein rings halos of light where the distant object's image gets warped into a complete circle around the lensing galaxy. Some of the most breathtaking examples come from Hubble's Frontier Fields program, where galaxy clusters like Abell 1689 amplify the light of galaxies over 13 billion light-years away. These clusters, weighing as much as a quadrillion suns, magnify their background targets by up to 50 times, bringing into focus galaxies so faint they'd normally be invisible even to our most powerful telescopes. One such lensed galaxy, nicknamed the Sunburst Arc, appears in 12 separate duplicated images around the cluster, its starlight stretched and twisted like reflections in a funhouse mirror. But lensing isn't just about pretty pictures, it's one of astronomy's most powerful tools. By analyzing how light distorts around a foreground galaxy, scientists can map its dark matter distribution with precision, revealing how this invisible scaffolding shapes galactic growth. Lensing also lets us measure the universe's expansion rate independently of other methods, testing whether our cosmological models hold up across vast distances. And in rare cases like the El Gordo cluster, lensing has exposed discrepancies between visible matter and gravitational effects, hinting at exotic physics waiting to be discovered. The most mind-bending aspect, lensing creates a cosmic time machine. When we observe a lensed galaxy, we're seeing multiple versions of it from slightly different moments in its history, thanks to the varied paths its light takes around the lens. It's as if nature handed us a flipbook of a galaxy's evolution, with each warped image representing a slightly different page. What began as a curious prediction in Einstein's equations has become a window into the universe's deepest secrets, proving that sometimes the cosmos bends the rules to give us a clearer view of itself. The Magellanic Clouds, those two ghostly smudges of light visible from the southern hemisphere, aren't just passing neighbors to the Milky Way. They're destined to collide with our galaxy in a celestial reunion that will ignite a firestorm of new stars, rewriting our galactic landscape forever. Right now, these dwarf galaxies orbit the Milky Way at distances of about 160,000 and 200,000 light-years, their gravity already warping the outer edges of our galaxy's disk. But their journey is spiraling inward, pulled by the same relentless force that's shaped cosmic structures since the dawn of time, gravity's unyielding tug. What makes this impending merger so extraordinary is the sheer volume of gas the Magellanic Clouds carry. Unlike many satellite galaxies stripped bare by previous encounters, the large and small Magellanic Clouds are brimming with hydrogen, enough to birth billions of new stars. As they're torn apart over the next 2 to 3 billion years, their gas will flood into the Milky Way's outer regions, compressing under shockwaves to form vast stellar nurseries. Imagine a cosmic waterfall cascading into an empty basin, only instead of water, it's the raw material for future suns. The signs of this slow-motion demolition are already visible. A sprawling river of gas known as the Magellanic Stream arcs across the southern sky, stretching over 600,000 light-years, a trail of cosmic breadcrumbs left as the cloud's gravity wrestles with the Milky Way's pull. Meanwhile, a younger structure called the leading arm is charging ahead of the clouds, its gas already raining onto our galaxy's disk. Radio telescopes have spotted pockets of this gas collapsing into star-forming regions, offering a preview of the fireworks to come. But this merger won't be a gentle embrace. The Milky Way's tidal forces will shred the Magellanic Clouds, twisting them into elongated streams of stars and gas. Their cores may survive as distinct clumps for a while, orbiting like bees around a hive, but eventually they'll dissolve into the Milky Way's halo. The large Magellanic Cloud, being more massive, will put up a fiercer fight. Its gravity might even warp our galaxy's disk further, amplifying the Milky Way's already warped edges into more pronounced twists. The real spectacle will unfold in the galactic outskirts. With fresh gas flooding in, the Milky Way's star formation rate could spike dramatically, particularly in the outer disk where material accumulates. Future astronomers, if any are around to witness it, might see new spiral arms forming, their blue-white stellar populations blazing against the older, yellower backdrop of our current disk. Supernova from short-lived massive stars will seed the gas with heavy elements, enriching future generations of stars and planets. Yet this merger carries an ironic twist. The same gas that fuels stellar birth could also awaken our galaxy's sleeping monster Sagittarius, a star, the supermassive black hole at the Milky Way's heart. If enough gas spirals inward, it might trigger a quasar-like outburst, flooding the galaxy with radiation that could sterilize newly forming planetary systems. It's a cosmic balancing act. Too much inflow and the black hole's fury might stifle star formation. Too little and the galactic suburbs remain dark. The Magellanic Cloud's fate mirrors countless similar mergers that built galaxies like ours over cosmic time. They're a reminder that no galactic island is truly isolated. Gravity ensures that even the most distant companions are dancing toward an inevitable collision. When the final act plays out, their stars will mingle with ours in a silent, slow-motion fireworks display, their legacy written in the newborn stars that light up the Milky Way's future. For now, these clouds drift lazily across our skies, giving no hint of the chaos and creation their merger will unleash. But in the grand timeline of the cosmos, their collision is already in motion, a testament to the universe's endless cycle of destruction and rebirth, where even the smallest galaxies can leave the brightest marks. Deep in the heart of countless galaxies, supermassive black holes don't just consume matter, they transform it into cosmic geysers, blasting jets of energy so powerful they can sterilize entire galactic neighborhoods. These aren't gentle streams, but scalding eruptions of plasma and radiation, shooting outward at nearly the speed of light and stretching for hundreds of thousands of light years. When these jets slam into surrounding gas clouds, they don't just push them aside, they superheat the material to millions of degrees, rendering it too energetic to collapse into new stars. It's like turning a nursery into a furnace where the very ingredients for stellar birth are vaporized before they can coalesce. Take the galaxy cluster MS 7035, where a black hole's jets have carved colossal cavities in the surrounding hot gas, each bubble large enough to swallow 600 Milky Ways side by side. The energy required to create these voids is staggering, equivalent to 1 trillion supernovae. But instead of destruction, this eruption has a paradoxical effect. By preventing gas from cooling and forming stars, the black hole regulates its galaxy's growth. Without these outbursts, the central galaxy in MS 7035 might have exhausted its fuel eons ago, burning through its gas in an unsustainable frenzy of star formation. The mechanics behind these jets read like something from a sci-fi novel. As matter spirals toward the black hole, intense magnetic fields coil around it like cosmic slingshots, channeling some of the infalling material into narrow beams along the black hole's spin axis. These jets, composed of electrons and protons accelerated to near light speed, glow fiercely in radio waves as they plow through intergalactic space. In some cases, like the famous M87 galaxy, these jets punch completely out of their host galaxy, visible from 55 million light-years away. But here's the twist: these jets don't just suppress star formation, they can also trigger it. When the jet's shockwaves encounter particularly dense gas clouds, the compression can ignite stellar birth at their edges. It's a cosmic irony. The same force that sterilizes vast regions also creates pockets of intense star formation, like a wildfire that simultaneously burns a forest and fertilizes the soil for new growth. The galaxy Centaurus showcases this duality, with strings of young stars lining the outer fringes of its dark, jet-carved lanes. What's truly mind-bending is how these black hole geysers scale with their host galaxies. Observations reveal a tight correlation between a galaxy's mass and its central black hole's energy output, as if nature hardwired a feedback loop to maintain balance. Too much star formation, the black hole activates, heating the gas and slowing things down. Too quiet, the jets subside, allowing gas to cool and star formation to resume. This cosmic thermostat ensures galaxies don't burn too bright and fast or fade into obscurity too soon. Yet sometimes the system goes haywire. Quasars, black holes in hyperactive feeding frenzies, can unleash jets so powerful they blow away a galaxy's entire gas supply, effectively dooming it to a slow, starved demise. The galaxy Markarian 2316 appears caught in this overactive state, its black hole's jets shredding surrounding clouds into hot, useless wisps. It's a stark reminder that even the most finely tuned cosmic mechanisms can spiral out of control, with consequences lasting billions of years. New telescopes are revealing how these jets shape not just individual galaxies, but the cosmos at large. The Event Horizon Telescope, famous for imaging a black hole's shadow, now studies how jets launch at their source. Meanwhile, the Chandra X-ray Observatory traces how their energy dissipates through galaxy clusters, redistributing heavy elements and sculpting the universe's large-scale structure. These observations paint black holes not as passive monsters, but as active architects, their geysers carving voids and seeding new growth across the cosmic web. So the next time you see an image of a galaxy with brilliant jets spewing from its core, remember, you're witnessing one of the universe's most potent regulatory forces in action. These aren't just spectacular light shows, they're the pulse of galactic evolution, proof that even the darkest objects can illuminate the delicate balance that shapes everything we see in the night sky. Astronomers face a cosmic blind spot when trying to peer into the universe's most tumultuous years, a mysterious gap in galactic history nicknamed the redshift desert. This frustrating observational void spans the period between 2 and 3 billion years after the Big Bang, when galaxies were undergoing radical transformations but remain frustratingly difficult to study. The problem isn't that galaxies didn't exist back then. It's that their light gets lost in a technical no-man's land between detection methods. The culprit lies in how we measure cosmic distances. Astronomers rely heavily on redshift, the stretching of light to longer, redder wavelengths as space expands, to determine how far away an object is. For galaxies in this awkward, adolescent phase, their light redshifts into an awkward middle ground where it's too faint for optical telescopes like Hubble to capture clearly, yet not redshifted enough for infrared telescopes to pick up efficiently. It's like trying to tune into a radio station that keeps slipping between two frequencies. You catch bits and pieces, but never the full picture. What makes this era so crucial and so frustrating to miss? These were the universe's formative years when galaxies shifted from chaotic, gas-rich youth to the more structured maturity we see today. Star formation rates peaked, black holes began regulating galactic growth, and spiral arms started stabilizing. Some of the most dramatic transitions in cosmic history unfolded during this window, yet our view remains fragmented. Ground-based surveys have attempted to bridge the gap with painstaking observations, like the Vilti Deep Survey, which laboriously catalogued thousands of galaxies in this redshift range. Their findings suggest galaxies during this epoch were factories of activity, merging frequently, ejecting gas through supernova, and birthing stars at rates 10 times higher than today. But these glimpses are like snapshots of a fireworks display taken through thick fog. You see the bursts of light but miss the intricate connections between them. The James Webb Space Telescope is beginning to change the game. With its unparalleled infrared sensitivity, Webb can detect the redshifted light from this era that previous telescopes couldn't. Early observations already reveal surprises like galaxies with mature structures appearing earlier than expected, and black holes whose growth seems out of sync with their host galaxies. Each new data point chips away at the desert's barriers, turning what was once a wasteland of missing knowledge into a frontier ripe for discovery. Yet even as technology improves, the redshift desert reminds us of a humbling truth: the universe doesn't reveal its secrets easily. Some chapters of cosmic history are written in wavelengths just beyond our reach, their stories waiting for the right tools to bring them into focus. What we've learned so far is merely the preface. The full narrative of galaxies coming of age remains half buried in the sands of this elusive cosmic desert. Most galaxies play by the rules with a single supermassive black hole anchoring their core, but cosmic rebels like Messier 83 break the mold with a startling secret: two monstrous black holes circling each other like celestial prizefighters in the galactic arena. This rare phenomenon, known as a dual-active galactic nucleus, occurs when galaxies merge but their central black holes refuse to immediately coalesce, instead engaging in an orbital dance that can last for hundreds of millions of years. Messier 83, a face-on spiral galaxy 15 million light-years away, showcases this cosmic pas de deux in spectacular fashion. Observations from the Chandra X-ray Observatory reveal two brilliant X-ray sources separated by just a few hundred light-years, telltale signatures of supermassive black holes feeding on surrounding gas. What makes this pair extraordinary isn't just their proximity, but their contrasting appetites. One gorges voraciously, spewing jets of high-energy particles, while its companion dines more modestly, flickering like a candle in the cosmic wind. This mismatched behavior offers clues about their violent origins, likely the remnants of a smaller galaxy plunging into Messier 83's disk long ago, its core black hole still resisting full assimilation. The physics behind these stalled mergers is mind-bending. When galaxies collide, their black holes sink toward the new galactic center through a process called dynamical friction. But once they're within about 1 parsec of each other, the surrounding stars thin out, leaving little material to further break their motion. At this point, the black holes enter what astronomers term the final parsec problem, a gravitational standoff where they might circle each other for eons before finally merging in a universe-shaking burst of gravitational waves. Some systems never complete this final step, remaining as permanent binary threats at their galaxy's heart. Infrared studies of other double nuclei galaxies, like NGC 6240, show even more complex dynamics. There, the twin black holes, separated by just 3,000 light-years, have each ignited starburst rings around themselves, creating concentric circles of newborn stars that bloom like ripples from dual pebbles dropped in a pond. These rings act as cosmic breadcrumbs, tracing the shock waves of infalling gas compressed by the black holes' opposing gravitational pulls. The eventual fate of these dueling behemoths depends on their surroundings. In gas-rich environments like the luminous infrared galaxy ARP 220, the black holes may spiral together faster as viscous drag from surrounding material siphons away their orbital energy. In quieter galaxies, they could remain locked in their dance until random stellar flybys gradually rob them of momentum, a process stretching longer than the current age of the universe. What's truly astonishing is how these systems reshape their host galaxies. Twin black holes don't just orbit passively, their gravitational punches slingshot nearby stars into chaotic trajectories, creating zones of hypervelocity stars fleeing the galactic core. Meanwhile, their combined energy output can carve vast cavities in interstellar gas, alternately quenching and igniting star formation across entire galactic sectors. Some theorists suggest double nuclei might even explain peculiar galaxy shapes, their gravitational tides twisting spiral arms into pretzel-like knots. The most spectacular endgame comes when, or if, the black holes finally merge. Computer simulations show their last moments would unleash energy exceeding 100 million supernova, warping spacetime itself with gravitational waves detectable across the cosmos. LIGO observations of smaller black hole mergers hint that such events might kick the resulting behemoth clear out of its host galaxy, a cosmic ejection leaving behind a baffling, black hole-less galaxy for future astronomers to ponder. For now, double nuclei galaxies remain cosmic puzzles wrapped in enigmas. Each discovery, from Messier 83's odd couple to the triple black hole system in NGC 6240, challenges our assumptions about galactic evolution. They're reminders that the universe loves breaking its own rules, turning what should be straightforward mergers into drawn-out dramas of gravity, time, and unresolved endings. The Milky Way wasn't born alone. It emerged from a colossal nursery of gas and dark matter alongside thousands of sibling galaxies, most now scattered across the universe like seeds in a cosmic wind. Picture the early universe as a vast, churning sea of hydrogen, where dense patches of gas collapsed under their own gravity, fragmenting into smaller clouds that would become galactic building blocks. Our galaxy formed from one such fragment, but the rest, its true siblings, have long since drifted into the darkness, carried away by the expansion of space and gravitational tugs from neighboring structures. Tracing these lost relatives isn't just about solving a family mystery. It's a window into how galaxies evolve in isolation versus those like ours that grew up in crowded environments. Clues to this scattered family lie in stellar chemistry. Stars born from the same primordial cloud share a distinct chemical fingerprint, a specific ratio of elements like oxygen, iron, and magnesium forged in the universe's first supernova. Astronomers have found a handful of these chemical siblings within the Milky Way's halo, such as the stars of the Fermy stream, whose composition and motion betray their extragalactic origin. These interlopers likely came from smaller galaxies that merged with ours, but the hunt continues for true siblings galaxies that formed alongside the Milky Way yet escaped absorption. One candidate, the distant spiral galaxy UGC 12787, shares an uncanny resemblance to our galaxy's predicted early structure, from its metal-poor halo to the arrangement of its oldest globular clusters. The search is complicated by the cosmic web's relentless expansion. Over 13 billion years, galaxies born in the same neighborhood could now be separated by billions of light years. Supercomputer simulations like the Illustris TNG project attempt to reconstruct these dispersal patterns by modeling the gravitational forces that shape the universe's large-scale structure. These simulations suggest the Milky Way's siblings might reside in a broad ring around the so-called Laniakea supercluster, drifting along filaments of dark matter like beads on an invisible string. Some may even be hiding in plain sight galaxies like M94, whose unusual star-forming ring and compact core match predictions for how the Milky Way's siblings would appear after eons of independent evolution. What's fascinating is how differently these siblings might have aged. Isolated galaxies, free from the tidal pulls and mergers that shape the Milky Way, could have evolved into serene, undisturbed spirals with delicate, symmetric arms. Others, perhaps captured by massive galaxy clusters, might have been stripped of their gas and transformed into faint, ghostly ellipticals. A few could have collided with neighbors, birthing luminous starburst galaxies that burned brightly before quenching into red, dead relics. This diversity would offer a natural experiment. By comparing these siblings to the Milky Way, astronomers could isolate which features of our galaxy, its barred spiral structure, its satellite system, even its habitable planets, are products of its unique history versus traits inherited from its birth environment. The most tantalizing possibility is that some siblings host life. If the Milky Way's chemistry and stability allowed Earth to form, why wouldn't the same conditions arise in galaxies born from the same gas cloud? The odds are slim we'll ever find out. The nearest suspected sibling could be tens of millions of light years away, but the idea reshapes our cosmic perspective. We're not just inhabitants of the Milky Way, we're the products of a galactic lineage stretching back to a single, long-vanished cloud of gas. Every star we see, every exoplanet discovered, might have distant cousins in galaxies we'll never map, their own stories unfolding in parallel to ours. This search for lost siblings isn't just about cataloging galaxies, it's about reconstructing the Milky Way's origin story. Like an adoptee piecing together their past from scattered records, astronomers use chemical clues, stellar motions, and supercomputer simulations to reunite a family scattered by time and space. And with every new telescope, from the James Webb Space Telescope to the upcoming Vera Rubin Observatory, we peel back another layer of this cosmic genealogy, inching closer to answering one of astronomy's most haunting questions: who and where are our galaxy's forgotten twins? Galaxies don't always rely on violent collisions or cosmic winds to fuel new stars. Sometimes the universe delivers its gifts gently, like a quiet summer rain. Imagine a galaxy that's exhausted its gas supply, its star formation slowed to a trickle, its spiral arms fading into a dull red glow. Then, out of the void, cool clouds of hydrogen begin to drift inward, condensing and falling into the galactic disk like a celestial downpour. This phenomenon, called galactic rain, isn't just poetic. It's a critical mechanism for rejuvenating aging galaxies, offering them a second chance at cosmic relevance. The process starts in the vast, invisible reservoirs surrounding galaxies, enormous halos of hot gas that stretch hundreds of thousands of light years into intergalactic space. Over time, pockets of this gas can cool, especially where denser filaments of the cosmic web funnel material inward. As temperatures drop, atoms slow down and clump together, forming clouds dense enough to resist the halo's scorching heat. Gravity then takes over, pulling these clouds toward the galactic disk in a slow-motion cascade. Unlike the chaotic bursts of star formation triggered by mergers, this rain arrives steadily, a nourishing drizzle that can last for billions of years. One of the most dramatic examples unfolds in the nearby Sombrero Galaxy. Observations from the Chandra X-ray Observatory reveal a halo of million-degree gas, but nestled within it are tendrils of cooler, star-forming material, evidence of a constant, gentle inflow. These cold streams slip through the hot halo like sleet through fog, eventually reaching the galaxy's disk and igniting pockets of stellar birth. It's a delicate balancing act. Too much heat and the gas evaporates, too little, and it floods the galaxy with more material than it can handle. But galactic rain isn't always peaceful. In massive galaxy clusters like Virgo, infalling gas can get shredded by tidal forces, creating a phenomenon known as cold mode accretion. Here, the gas doesn't fall smoothly. It fragments into massive, moon-sized droplets that plummet toward the central galaxy at hundreds of miles per second. When these droplets hit, they don't just spark star formation. They can also trigger shock waves that ripple through the interstellar medium, compressing existing clouds and launching new waves of stellar nurseries. The Galaxy NGC 4696 showcases this beautifully, with X-ray images showing a trail of cooling gas arcing toward its core like a waterfall feeding a lake. What's fascinating is how this process interacts with a galaxy's supermassive black hole. In some systems, like the nearby elliptical galaxy NGC 5578, the infalling gas doesn't just feed stars, it also revives dormant black holes. As cool gas swirls into the galactic center, it can reignite quasar-like activity, creating a feedback loop where the black hole's outbursts heat the halo, temporarily shutting off the rain. This self-regulating cycle ensures galaxies don't grow too quickly or too slowly, maintaining equilibrium over cosmic timescales. Yet the most astonishing discoveries come from the far reaches of the universe. The James Webb Space Telescope has spotted ancient galaxies where cold gas streams appear to be the primary fuel source, their star formation sustained not by violent mergers but by these quiet, persistent inflows. This challenges the long-held assumption that only dramatic collisions could power the universe's early stellar booms. Instead, it seems some galaxies thrived on patience, drawing nourishment from the cosmic web like roots tapping into an underground spring. Galactic rain reminds us that the universe operates on multiple rhythms, not just the explosive crashes of colliding giants, but also the slow, sure cadence of material cycling back to where it's needed most. It's a testament to nature's ability to balance chaos and order, ensuring that even the quietest processes can reshape galaxies over time. And for astronomers, these cold streams offer hope, proof that even the most faded galaxies might one day bloom again, given enough time and the right conditions. Most galaxies cluster together like guests at a cosmic party, but not MCG plus 01-02-015. This lonely spiral floats in what astronomers call a void, an unfathomably empty region where the nearest galaxy might be 100 million light-years away. Imagine standing alone in a desert so vast the next person could be on another continent. That's the isolation this galaxy endures. Yet against all odds it thrives, a solitary island of stars adrift in an ocean of nothingness. How does a galaxy form in such emptiness? The prevailing theory suggests these void galaxies are relics of the early universe, born from rare overdensities in regions where dark matter failed to clump like it did elsewhere. While most galactic building blocks merged into bustling clusters, these stragglers remain behind, like the last uncollected pieces of a cosmic puzzle. MCG plus 01-02-015's pristine environment offers a unique laboratory. Its gas hasn't been stripped by violent collisions or heated by neighboring galaxies, preserving conditions similar to the universe's primordial simplicity. This isolation leaves a distinct imprint. Void galaxies often rotate more slowly than their cluster counterparts, their lazy spirals unperturbed by gravitational nudges. Their stars tend to be older and metal-poor, lacking the chemical enrichment from frequent galactic interactions. Yet paradoxically, some void galaxies like UGC 3672 sport vibrant blue disks, proof that even in the cosmos's quietest corners, gas can still collapse into newborn stars without the triggers of collisions or tidal forces. The voids themselves are marvels of cosmic architecture. These bubbles, some spanning hundreds of millions of light-years, make up the universe's large-scale structure alongside galaxy filaments and clusters. Simulations suggest voids aren't completely empty. They contain a sparse scattering of dark matter and hydrogen, a whisper of the cosmic web's scaffolding. Galaxies like MCG plus 01-02-015 might cling to faint dark matter tendrils threading the void, their stars the only visible markers of an otherwise invisible framework. What's startling is how these loners challenge our understanding of galactic evolution. Without the constant bombardment of neighboring galaxies, void galaxies evolve at their own unhurried pace. Some appear frozen in time, their structures unchanged for billions of years, while others undergo mysterious bursts of star formation defying traditional models. The galaxy ESO 406-043, for instance, floats in a void yet boasts a star-forming ring, likely fueled by a reservoir of gas that survived unperturbed since the universe's youth. Void galaxies also serve as cosmic control experiments. By studying them, astronomers can disentangle the effects of environment from the innate processes driving galactic growth. For instance, the prevalence of supermassive black holes in these isolated systems suggests these monsters might form through mechanisms unrelated to galactic collisions, perhaps seeded directly from collapsing gas clouds in the early universe. The most profound lesson these hermits teach us: isolation doesn't mean stagnation. Against the backdrop of a nearly empty universe, galaxies like MCG plus 01-02-015 continue to spin, evolve, and even birth new stars, proof that the drive to create isn't limited to the crowded metropolis of galaxy clusters. In the grand tapestry of the cosmos, these solitary threads remind us that even the quietest places can harbor their own kind of cosmic brilliance. The universe as we know it is living on borrowed time. The galaxies we see today, vibrant spirals bursting with star formation, massive ellipticals glowing with ancient stars, are just a fleeting phase in a cosmic timeline stretching trillions of years into the future. As the universe expands and dark energy accelerates its pace, galaxies will face an inevitable transformation, their evolution dictated by dwindling resources and the slow but unstoppable pull of gravity. Picture the distant future 10 trillion years from now. The raw material for new stars' hydrogen gas has been almost entirely consumed or ejected into intergalactic space. Galactic mergers, once the architects of giant ellipticals, become rare as the space between galaxies stretches beyond reach. The Milky Way, long since merged with Andromeda and its satellite galaxies, will have exhausted its gas reserves, its once bright spiral arms faded into a featureless haze of aging stars. Star formation will have trickled to a near halt, with new suns igniting only when the occasional brown dwarf collides or a rogue gas cloud drifts into a galactic core. The universe's stellar nurseries will fall silent, leaving galaxies to dim under the weight of time. But the story doesn't end there. Even without fresh stars, galaxies will continue to evolve in unexpected ways. As stars burn out, the heaviest survivors, red dwarfs, will dominate. These tiny, miserly stars, some with lifespans exceeding 10 trillion years, will outlast all others, their faint red glow the last light in an increasingly dark cosmos. Meanwhile, stellar remnants, white dwarfs, neutron stars, and black holes will gradually accumulate, their gravitational interactions flinging lower mass stars into the void or sending them spiraling toward their doom. Over eons, galaxies will evaporate, losing stars through these chaotic encounters until only a dense core of black holes remains, orbiting one another in a final, slow dance. The most massive galaxies, those already settled into elliptical forms, will face a different fate. Without new mergers to rejuvenate them, their supermassive black holes will grow quiet, their accretion disks starved of fresh material. Yet even in dormancy, these black holes will still shape their surroundings. As stars are ripped apart by tidal forces or stray too close to the event horizon, the resulting flares, though rare, will briefly light up the galactic core. Over time, the black holes themselves may merge, their collisions sending gravitational waves rippling through a universe otherwise devoid of fireworks. But perhaps the most profound change will be the universe's increasing isolation. As cosmic expansion accelerates, galaxies beyond our local group will vanish beyond the observable horizon, their light stretched beyond detection. The night sky, once filled with distant galaxies, will grow emptier, leaving future civilizations, if any still exist, with no evidence of a universe beyond their own lonely galactic island. The Milky Way and Andromeda's merger remnant, alongside a handful of dwarf galaxies, will be all that remains visible, adrift in an eternal sea of darkness. Yet even in this distant era, traces of today's universe will linger. The heavy elements forged in long-dead stars, carbon, oxygen, iron, will still drift through space, remnants of a time when galaxies blazed with light. Planets, though cold and lifeless, may endure, their silent orbits a testament to a once vibrant cosmos. And though star formation may cease, the universe's story isn't truly over, just transformed. The galaxies we know now will fade, but their legacy will echo across eternity, written in the slow, inevitable workings of gravity, entropy, and time. For now, we live in the universe's golden age of galaxies, a brief, luminous moment when starbirth still lights the darkness, collisions reshape cosmic landscapes, and the night sky teems with distant suns. The future may be cold and dark, but it's a reminder to cherish the cosmic spectacle we're privileged to witness, a fleeting chapter in the grand story of everything. Every atom in your body, the calcium in your bones, the iron in your blood, even the oxygen filling your lungs, carries a cosmic origin story written in starlight. We aren't just observers of the universe, we're literal stardust shaped by billions of years of galactic alchemy, the carbon that forms the backbone of your DNA. Forged in the fiery hearts of dying stars, the gold in your jewelry, cast into the cosmos by colliding neutron stars, the very elements that make life possible were scattered across space by supernova explosions, stellar winds, and galactic collisions, processes that turn the primordial soup of hydrogen and helium into the rich chemical tapestry we take for granted today. Consider this: the iron coursing through your veins likely began its journey in a supernova that detonated more than 5 billion years ago, before our solar system even existed. When that massive star reached the end of its life, it didn't fade quietly. In its final moments, temperatures in its core spiked to unimaginable levels, fusing atoms into heavier elements like iron and nickel. Then, in a cataclysmic explosion, it blasted these newly forged ingredients into the surrounding gas clouds. That stellar debris mixed with interstellar material, eventually collapsing under gravity to form new stars, including our Sun and the planets that orbit it. Without that violent stellar death, Earth's metallic core might never have formed, leaving our planet without the magnetic field that protects life from cosmic radiation. But stars aren't the only cosmic factories contributing to our existence. Look at the iodine in your thyroid or the uranium deep in Earth's crust. These heavier elements likely owe their origins to neutron star mergers, collisions so violent they warp the fabric of space-time. When these ultra-dense stellar remnants spiral together, they create conditions so extreme that protons and neutrons are crushed into new configurations, seeding the universe with rare elements. The 2017 detection of gravitational waves from such a collision codenamed GW170817 gave us front-row seats to this cosmic foundry in action. Telescopes observed the aftermath glowing with newly synthesized gold and platinum, proving these events are celestial jewelry shops on a galactic scale. Galaxies act as the universe's ultimate recyclers, gathering these scattered elements and weaving them into new generations of stars and planets. The Milky Way spiral arms, for instance, aren't just beautiful swirls of starlight. They're mixing bowls where supernova remnants and stellar winds churn together, enriching the galaxy's gas with life-friendly elements. Our solar system formed in one such enriched region, a fortunate location where previous stellar generations had stockpiled the necessary ingredients for rocky planets and ultimately life. Even the water filling Earth's oceans may have interstellar origins, its hydrogen atoms dating back to the Big Bang and its oxygen forged in ancient stars, combined in icy grains that hitched rides on comets. This grand chemical legacy connects us to the most spectacular events in cosmic history. The nitrogen in your DNA might have formed in a red giant star's slow burn. The phosphorus in your bones could trace back to a supernova shockwave compressing a nearby molecular cloud. Even the zinc that powers your immune system might have spent eons drifting through galactic fountains ejected from the Milky Way's disk by stellar explosions, only to rain back down billions of years later. So when you gaze at the night sky, remember, you're not just looking at distant points of light. You're seeing the factories that built you the stellar forges, the galactic recycling centers, the violent collisions that turned simple atoms into the building blocks of life. Every breath you take contains oxygen atoms created in stars that died before Earth existed. Every step you take presses phosphorus from supernova debris into the soil beneath your feet. We are, in the most profound sense, the universe's way of understanding itself, a collection of ancient stardust woven together by time and gravity into conscious beings capable of tracing our own cosmic origins. The next time someone calls you star stuff, smile. It's more than poetry. It's the literal truth. From the quantum ripples that birthed the first galaxies to the supermassive black holes sculpting their futures, we've journeyed through 50 astonishing truths that reveal our universe as a living, breathing entity, constantly rewriting its own story. These aren't just distant phenomena, they're the cosmic fingerprints shaping everything from the atoms in your hands to the light from stars that died before Earth existed. Each fact peels back another layer of time, showing how galaxies evolved from fragile clouds of primordial gas into the magnificent spirals and ellipticals we admire today, only to fade, collide, or transform again over eons. Consider the scale: dark matter's invisible scaffolding, stretching millions of light years to cradle galaxies. The violent beauty of galactic mergers where destruction births new stars. The supermassive black holes lurking in galactic cores, capable of sterilizing entire regions with their outbursts, yet somehow fostering star formation in their wake. These processes unfold on timelines so vast they dwarf human history, yet every one leaves traces we can decode, from the warped edges of the Milky Way to the ghostly streams of stars torn from cannibalized dwarfs. What's truly humbling is how interconnected it all is. The iron in your blood, the calcium in your bones, they were forged in stellar furnaces and scattered across space by supernova, only to be gathered into new solar systems by the same gravitational dances that shape galaxies. Every time you gaze at the night sky, you're witnessing a snapshot of this grand evolution. The Andromeda galaxy barreling toward us for a future collision, the faint glow of the Magellanic clouds being slowly unraveled by the Milky Way's gravity, the distant pinpricks of light from galaxies that may already be dead, their light just now reaching us. So tonight, step outside, look up, let your eyes adjust to the darkness until the Milky Way emerges not as a static painting, but as a dynamic, ever-changing structure. Each star you see is a character in this epic, and you, yes, you are part of it too. stardust given consciousness contemplating the very forces that made it. If that doesn't take your breath away, nothing will. Want to keep exploring the cosmos's greatest mysteries? Hit subscribe and join us as we unravel more celestial wonders. The universe has countless stories left to tell, and the next one might just change how you see